Okay, everything is okay because I see some things appearing on my screen. Okay.
Yeah, you are asked if you give permission for recording. And you have to click
okay.
in order to.
Perfect. Yeah. Okay, so I will talk about the characterization of amorphous silica using DFT methods, and so also the derived properties of this material. This is the outline, or let's say the large outline, because I think I will not be able to see everything, but I will pick some, as I said before, I will pick some points out of it. The different topics or subjects I've studied in the last, let's say, 15 years have been reviewed in 2 papers, which you can see at the right side of your screen. So I will talk first about how to make a silica, amorphous silica model when you use ab initio or DFT methods, and then improving these models, making it more realistic, going to mesoporous materials like MCM41, and then a series of applications. As you can see here, it goes about catalysis, adsorption, also nanoparticles. So first of all, what is amorphous silica? So it's better like this, yeah. What is amorphous silica? So, well, this occurs in nature, but also synthetic. So naturally, maybe you know them. It's well, you have the flintstone, used by mankind for many millennia. Then you have opal, which is the I don't know if you see my arrow, my cursor, which is well, also used for many centuries in jewelry. And then you have also, these are organic examples, but you have also, let's say, examples coming from the biological world, which are the shells of diatoms, which is from biological origin. Yeah? So these all contain amorphous silica. But next to that, you have also synthetic amorphous silicas. And this is, well, I don't have so fancy figures pictures to show you, but it's mainly powders or colorless material. And this can be synthesized in different ways. So you can produce this in wet process, or in thermal pyrogenic airborne fumed silica, arc furnace silica, and so on. These silicas have a lot of applications, so we can use them, well, for many years already used as reinforcers and fillers in different materials, also in paints, varnishes, and so on. Here we are mainly interested in the use in the properties which are related to adsorption and reactivity. So we find them also in pharmaceutical applications. And as a support in heterogeneous catalysis. So our model, well, we started studying this amorphous silica, well, in the beginning of the years 2000, and we published our first model, characterized and compared with experiment. This will come back many times because we work very closely in collaboration with experimentalists. As you will see also, or I hope I can make it clear that amorphous structures, it's very difficult to do this only with theoretical data, because they are very dependent on the way how you make the material, the way of synthesis. So we start from coordinates that were obtained, well, before, let's say, the era when DFT, ab initio calculations on large systems and in solid state were already common, before we used force fields. And there existed already some structures, but mainly bulk. So without any surface, let's say, interfaces, so no crystal ending. But the coordinates of large systems obtained for bulk silica existed, namely the group of Bernasconi in Italy, who was active in that. So we used these coordinates and picked out a model or a part, let's say a unit cell, that contained, well, a reasonable number of atoms that was that we could calculate. This was the important. We wanted to have a realistic but also a calculable model. Okay, it was the aim to use it after that in different applications. So this once we have this box cut out of a force field obtained silica, we relaxed it and we modified it also. We modified it by hand, trying to simulate the results that were obtained experimentally by the characterizations. So the surface of the silica, the interface, this is what is in fact the important property if you want to study reactivity of silica. So we saw directly that the importance of silanols, which are the OH groups, which are on the silica surface, they play the important role here in the different chemical and physical properties. So this was characterized by, well, vibrational spectroscopies, NMR, and also colorimetry by hydration. The history of the different models of amorphous silica well, started in 2008. We published one model almost simultaneously with another group, the group of Ugliengo in Italy in 2008 also. Then we have to wait some years, and then in the United States also there appeared a model by Ewing and et al. In 2014, and then in 2016, more recently, we have the model of EPS-CMD from ETH. So here I show you some results we used, the experimental results that we used to make this model. So it's mainly the number of silanols, the silanol density, which is directly related with the hydration, degree of the hydration, and also the way how it is synthesized. Yes. This degree of hydration is translated into silanol densities, but you have different types of silanol densities, types of silanols, sorry. You have geminal silanols, vicinal, and isolated ones, and they can all be, well, characterized within a certain window of certainty, but what is sure is that there is a distribution among them, and this makes every silica characteristic. So we used one, and we tried to mimic the experimental results on our models, and this is done by doing it by hand and then relaxing it. Yeah? So we opened ring sizes, siloxane rings, which means that we dehydrated and hydrated by hand, and so placing the different hydroxyl groups off before a relaxation. All this was then, let's say, relaxed with molecular dynamics at the temperature that we wanted to use for our application. This model contains still used, contains about 260, 300 atoms. This is used in many studies in the beginning. Especially, we wanted to see the effect of the temperature on the silanol density, the effect of hydration. Then we could put some molecules on top on the surface. So we investigated the functionalization, which is also important for some catalytic and also absorption experiments. The effect of confinement was later on, where we wanted to simulate channels like the MCM, like the mesoporous silica, and then also substitution in the framework. So what happens when we substitute the silicon by another element? After that, we wanted to make our model and more realistic. We had a slab, it's good, it works. It is locally, it was proven that it was locally very efficient to represent the chemistry. So now we wanted to go to some 3D material. And so, well, here I show you how an MCM, a mesoporous silica, is synthesized. It starts, I don't know if I have to go too much into details, but it starts from an assembly of surfactants. You have kind of micelles which make like those rods. They assemble in an hexagonal symmetry, and around this structure of surfactants, you can grow a silica framework. You burn out the organic material and you are left over with what you see here, this hexagonal symmetry structure with these channels. So the idea is to make a model for this. And we come up with the following unit cell. So here what you see is that we have in fact assembled 3 of these slabs that contains these 260 to 300 atoms together into a special shape of unit cell. The main problem here was in fact to find the connections between those 3. If you see there are 3, so it's like making a Y, letter Y. So we have 1, 2, and 3, which comes together in the center here. And so the idea is to find connections between them. Yes. So we obtained that by molecular dynamics and relaxation afterwards. And we obtained this kind of structure. So our model is now 3 times, or a little bit more than 3 times bigger than before, than 8 years before. As you see, we published this structure in 2016. So from this structure, we could in fact start to analyze what is the effect of hydration in these kind of materials. Most of the time, if you do catalysis, you catalyze, you calcine the structure, so you dehydrate strongly. So then this means that the structure here changes also, because the silanols, which are there due to the interaction with water, leave the structure and form a siloxane bridge. So there is a kind of dynamic process at the surface. The opposite occurs when you hydrate completely the surface. So you go to a maximum of silanols at the surface. Here you see that we filled the vacuum. In fact, what will be the pore if you, what is the pore if you multiply the unit cell in 3D. So the interaction of water with our surface, and here we have the vacuum at a low hydroxyl density. So this is how it looks like when you multiply the unit cell. So we reproduce this hexagonal structure and these pores. Here you see again how the unit cells are organized. I don't want to go too much into details, but we can in fact have some let's say geometrical parameters for the different degrees of hydration of our model. Yes, so different parameters that can directly be compared with the experiment. This was the aim, of course. After that, we calculated a vibrational spectrum also with the aim to compare and to have some fingerprints to see what is the effect of water in these kind of systems, and also some thermodynamic structure. I will go on, especially on the thermodynamic calculations on the next part. I will present all the diagrams like this. So what we did here is that we built different structures with different hydroxyl densities, and we estimated the stability as a function of the temperature. So you can see that as a function of temperature, you will dehydroxylate if you lower the if you increase the temperature. Yeah. So we are in fact able to model silica at different temperatures, which is also important if you want to model catalytic reactions. So once we have these models, we use them in applications, as you said, and so I hope I will have the time. I'm not chronometering, having a chronometer here, but I would like to go rapidly over some applications here. So I will first look about the grafting of oxides, transition metal oxides. I don't think I will have time to talk about cold adsorption, but I will certainly spend some time on talking about the interaction of water with the surface, and then some pharmaceutical application. So what happens when an organic molecule interacts with hydrogen bond network of silica. So first of all, if you want to graft an oxide, or here in this special case, monomer, mono-oxide species, we need to find a grafting spot. And this is typically a spot where we have a high density of silanol sites. like you've seen here, what I've shown here, what I show here is the site where you have three silanols close to each other. We are in fact ready to accept the presence of a transition metal oxide, a monomer of a transition metal oxide. On this side, which is called also a silanol nest, we absorb this kind of species. The first study here that we did is the grafting of vanadium oxide, vanadium 5 oxide monomers that were grafted on the silica, which found a lot of applications. I don't go into details, but we were especially interested in the structure. What is the geometry of this kind of sites, and how does it evolve during the reaction or as a function of temperature? So we can graft this entity, so vanadium 5 here, which is an oxide, and we have also put some hydrogen atoms, so you have an hydroxy and oxo groups. So you can bind it with one bond or link, 2 and 3. So one, as you see, also it has an effect on the OH groups on the side, and it has so in fact we see that it's clearly dependent on the temperature and hydration. In fact, yeah. So from these calculating these structures, we can build the thermodynamic phase diagram as we've seen before, and also some vibration frequencies. These structures are typically characterized by vibration spectroscopy, and in particular Raman, which shows a very nice band for the very precise band is green here for the vanadyl bond, the V double bond O, oxygen. And the rest are in fact interactions with OH groups. Yes, 8 bonded, they can be free, and also the framework with the vanadium. So these zones were determined with theory, with DFT, and compared with experiments. So in fact, what we could see is that there is, let's say, an automatic or an equilibrium between hydrated and dehydrated states. So we see a shift going from these structures to these structures, and vice versa. This is the phase diagram. What is interesting here is that since in modeling we can invent, or we can do a very systematic study, and so beside grafting we can also insert. Although this will be, let's say, dependent experimentally, this will be dependent on the way how you synthesize it. So here what we can see is that, for example, a 4 coordinated vanadium might be quite stable, yes, before this 450K, but depending on the way you synthesize it, you will see it or not. So in the way the experiments were performed, we had not this type of structures. So we went to the grafted structures, so with 1, 2, and 3 linkages, and then we could also define the stability domains on the temperature axis. Another example is a niobium. Niobium silicas are also have also found a lot of applications in catalysis, and there we have both species, both type of species, which are the grafted ones that we've seen before for vanadium, but we have the substituted or inserted ones. So it shows much more links with the framework. And this was interesting because we studied, in fact, the effect of several sites together. What happens? Do they want to cluster, or do they want to be separate? And for that we built a double model. Oops, sorry. Yeah, we built a double model, introducing 2 sites at the same surface, and displacing, moving one niobium relative to the other one. Okay. On our surface, on our amorphous silica surface. And we studied the interaction between them, and we found out, in fact, that there was, let's say, a minimum at a certain distance. And this corresponds to the size of our unit cell, which means that it is, in fact, that the two niobiums want to be as far as possible from each other. We should know. We should also say that these, if you have a pair of niobiums, they also show a different coordination. They experimentally, it is also shown that you have a Lewis acid and a base pair, yeah. O minus and niobium plus side. Here again, the phase diagram, also made on the same way. So once you have the different structures, you can, and the degree of hydration, you calculate the energy and you can make a surface energy of that. And you plot it in this kind of diagrams. And another example was then the column next to the group 5 is group 6, which is a little bit more complex, because you have the possibility to make higher coordinations. And here we studied it very systematic with the aim to see and to solve a question which is asked for many years already, is these group 6 elements, when they are grafted on silica and they are in monomer species, they are monomer species, do they show oxo groups or hydroxo groups? So here for that we calculated every species and made some phase diagram. We did this for the 3 elements in group 6. So we did this for the chromium. Yeah, here it's quite simple one. You have an hydroxyl group here on this oxo, one with 1 link, 2 links, the deoxo, which is very famous in the reactivity here, with like a Phillips, which is used for the polypropylene synthesis. This is the Phillips catalyst. We went down the table, so from chromium we went to molybdenum, so we increase even more the complexity here because there are more types of systems that appear, and for wolfram, for tungsten, we have even more complex systems, yes? But we were able to define the domains of stability. Now, together with all this information, we were able to make the following conclusion for the group 6. If you see here, we have two families, which is important for the synthesis. We can graft species and we can insert species. For the grafted species, if you go down the table, chromium, molybdenum, tungsten, again, then we see that the most stable structures for chromium is with the deoxo at the temperature where we work, where the catalytic reaction works. For the inserted, we go then for molybdenum and tungsten. There's also interesting point is the ease, how easy it is to hydroxylate. So the reaction barrier to hydroxylate your site is easier for chromium and molybdenum compared to molybdenum. So we were able to characterize, to describe the reactivity of the sites. Last part, I don't know how much time I still have. Can someone help me? Because
you still have 10 minutes.
Okay, very good. Then I continue with this. So then after this group 6 elements, we also checked some other elements. The idea is, well, once you have this model, we can try to insert or graft well, the whole collection, the whole collection of transition metals, because they have all found applications in heterogeneous catalysis. And one of the topics here that were chosen together with experimentalists was the zinc, the topic on zinc oxide. So here again, we have zinc oxide, which is, let's say, much more limited in the number of grafting possibilities, because we have a much lower degree of oxidation. So we have 2, mainly a coordination of 2 direct, let's say, linked chemical links. So we grafted zinc oxide, ZnO, the Zn2 plus, on our surface, which is hydroxylated, and we make a link. Yeah, we make a silicon oxygen zinc hydroxide side. We can do the same, but by making 2 links. We can do silicon oxygen, zinc oxygen, silicon. Yeah? So we have two types of sites. We have, in fact, it's we can say, or we have an hydroxyl group on zinc, or we don't. And how is it? How does it reorganize itself? Because since it has only two sites and silicon is tetrahedral, so we have maybe the possibility to reorganize and to make a new geometry. And this is what we will see. So we did this also again systematic on different sites, different types of silanols also. The different neighbors, and here we see that the interaction with the neighbors through hydrogen bonds is important for the stabilization. Yes, so we have associated here the energies. This is also directly linked with the temperature and the degree of hydration. We can have a phase diagram, so we can clearly see at which temperature one species transforms into the other. But what for us was the most interesting part is that, in fact, the interaction distorts the structure in such a way that for a silicon, which is next to the zinc, we obtain here a pentacoordinated silicon, which is very interesting, or a very interesting defect in this structure, because defects are known to be important in reactivity. And we know also that in nature, we have sometimes some pentacoordinated silicon, but in structures which occur at high pressure. And here we found it by just grafting or putting a zinc oxide species next to a silicon in a special special situation. So this opens the door to synthesizing materials with amorphous silica with specific defects, interesting for catalysis. So here I wanted to make a kind of overview for what we know on transition metals grafted in the monomeric form. Through the transition metals, through the periodic table. So if we go from group 3 to group 12, the first elements, they have a lower coordination, as we've seen for zinc, so lower than 4. So we can expect maybe some reorganizations, as we've seen for zinc. Group 4, this is isomorphic, which is already known and studied with titanium, which is used in photocatalysis. So we can isomorphically substitute silicon. What we can investigate there is the effect of the substitution on the electronic structure, and directly linked to the stability. Is there a top concentration, upper concentration of the titanium in this structure or not? Then we have these group 5 and 6 that I showed you before. So there we have especially the competition between hydroxyl groups and oxo groups. The same for group 7 that we have not studied yet, but there we increase the possibility. Imagine that we have manganese 7, then we can even go further with the number of hydroxyl groups or oxo groups. Then we go back, we go down again in the coordination for the group 8. Lower than 4, so we will have defects, especially I expect that these sites can provoke defects in the silica. And then we have the metal groups with the noble metal, the coinage metals, which form nanoparticles mainly for gold. We have done the study for gold. And then the zinc that I've just shown you. So this is about our study on heterogeneous catalysis. So what happens when...
so 5 minutes.
Okay, so I stop with that and then we are ready. So the important point here is the presence of water on silica, which is quite an interesting question, because you know that silica here is amorphous, and on top of that you put another amorphous system, which is water. So you have an interface which is amorphous, and the question is, will we have an order or not? So it's you make order out of an amorphous environment. We studied this with molecular dynamics, initial molecular dynamics, and we showed then the different types of silanols that are present. Especially you have, from an interesting interaction point of view, you have a donor, hydrogen bond donor and hydrogen bond acceptor species. And these are distributed among or over the different sites. And there are quite important properties linked to that, especially what is known as the bimodal acidity property of silica. So you have different types of silica, silanols that I show here, and we can go to extreme sites. And we calculated pKa's of these silanols, and we found extreme values of 2.9 to 10.3, which shows here that you have basic acid and basic sites. So very extreme sites. So in fact, you have to take into account that you have different types and a distribution of types of silanols at the surface. Now, how the interaction with water occurs, I will go further. Here I will go fast, maybe, and I will stop after that. So one of the proofs that there is a strong interaction with water is the following example. When you make some, let's say, little shells of silica using a surfactant, we have here a formation of what is called a liposome. It's a double layer cell, and around that again you can grow a silica, which forms liposyl structures, which is shown here. And this is interesting for pharmaceutical properties, but I will not pharmaceutical interactions, not applications, but I have no time to discuss that. But what is important is that the characterization of this, what is the interaction with the silica? With that I will end. If you see here our surfactant, which has this polar head, yes, with non-polar alkyl chains, and it's interacting with silicon dioxide. So with NMR we can, for example, check or characterize the phosphorus here in our site, and we find one peak, one shift. So what does it mean? One shift means that there is only one site, yeah, one environment. And if you see here in the structure, I'll make an enlargement here instead, where you have the silicon, which is interaction with our heads, our polar heads, which is in blue. You have also the double layer, which is the other side, but there you don't have silica. There you have water. So in fact, what happens is that you have then two environments and not one, and the experiment shows only one. What does it mean to us is that, in fact, this water layer, okay, is there, but in fact you have a water layer between silicon and water also present. And this is an example, but I can show you many of them, is that this water layer is very typical and characteristic for silicon. In many applications, if you don't calcine, you always have the presence of a water layer on top of it. I think I will stop with this here. So here is the model we used with the different other calculations for the NMR shifts, the different situations. And I think I stop here. I stop with the acknowledgements like this. So we did this with different peoples in the last, well, I think 15 or maybe already 20 years. I hope so that you enjoyed it, and I thank you for your attention. Thank you very much.
Thank you very much, Frederic, for this very beautiful talk on treating quite difficult systems, amorphous systems, which are not easy actually to treat with DFT or ab initio methodology. So questions? I don't see if someone put questions, so maybe just unmute yourself and put the question. I'll start with a short question by myself, because these are quite extended systems. I mean, some amorphous system doesn't have a small unit cell. Wouldn't it be actually, and you look at, I would say, operation like hydration, wouldn't it be easy to use something like reactive force field, for example, to look at the interactions between, and the hydration process, because you could use something like Grand Canonic Monte Carlo with reactive force field, or even simply reactive force field, to look at this interaction, given the size and number of atoms you are looking at.
Indeed, this would be ideally. the chemistry of hydration in these systems, because it's chemistry, you break and make new bonds, new chemical bonds. This would be perfectly, or maybe it's ideal to study with reactive force fields. We have not chosen this. Why? Well, it's maybe historically our group is not so involved in this type of methods, and we use maybe a more difficult way. This is by using well, different models. Let's say checking the final states, yes, before and after the hydration. So that's why we, at a certain moment, I showed you at the phase diagram of five states, but there are 5 different models. So we made 5 new models for doing that, and we don't have, in fact, a mechanism. And this is maybe something that can be studied with these reactive force fields. This is true, and could give maybe some more information on kinetics, which is so important. But indeed, this is something. Well, I'm quite interested to continue to do that.
Okay. Other questions?
So I have a question, if I might.
Yes, please.
Can I? Yeah. I've seen. Thank you, Frederic, for the nice talk. I just have a small question about one of the slides, or maybe I missed it. I think it was about considering defects, and then I've seen some clusters of molecules. And then I would just ask to speculate on the size effects, because there are no surfaces actually. There are clusters of molecules probably analyzed by, I don't know, by MD. I think it was the slide.
Normally we don't use clusters. Maybe I can go to the slide you say. But we have not worked. All calculations were done with CP2K or VASP, so we don't use clusters. It's when you see a cluster, it's because maybe I have not shown the periodicity.
Okay, that might have been. So that was I was indeed. So we are talking about periodic structures, but not about clusters of.
No, indeed. I have not written any cluster. The thing here is about this, yeah. Okay, this is what you. In fact, it's taken out. It's taken out. Sorry, it's not a cluster. It's because you see that, for example, here it should continue, and I just cut out the sides out of the surface.
Okay. Yes. Then I would have asked about the side effect, but that's then it's answered. Thank you.
So we have time for maybe one more question.
Can you hear me? May I use the opportunity? Okay. I have first a very short technical question. So which functional are you using typically?
It's from the beginning, from very early, we already used PBE. And with the time, so PBE with VASP, plane waves, and we, at the end, it's not only a couple of, or maybe 5 years already, in 2016, so it's already some time. Then we started to use also the corrections for the dispersion, because we were more and more interested in the interaction with water and so on. So, but at the end, I want to say something that, because this is also in my benefit, is that even if we didn't do the dispersion corrections, let's say 15, 20 years ago, we see that the results in these structures, which are quite ionic, don't change so much. So qualitatively, well, the conclusions I made so many years ago are still valid. So this makes me quite happy. But of course, now we use the dispersion correction to make it more precise. And I think we cannot do any other calculation. We should follow the evolution of the calculation levels.
And a second, maybe also short question, once you show this slide again. So if I understood correctly, you do ab initio MD for all the systems. So the temperature that you show in this phase diagram is the simulation temperature of the MD.
Well, I would say yes, but maybe if you have, maybe it depends. Maybe it depends the system you're thinking of. But most of the time we use 300 Kelvin.
Okay, so can you then comment again what this temperature means in this phase diagram then?
yeah, the one that you see here. Well, in fact, this is a kind of function. It's here we don't calculate every structure at a different temperature. It's just a kind of extrapolation. So we have the effect of the number of water molecules, so the stoichiometry, which you have the two lines here, red and blue, and you have also the effect of we calculate here a free energy. Yeah? So we have the insert also the entropic factor, but this is only done for water, not for the solid. So it's an approximation.
Okay.
And in fact, it's nothing more than a linear function, which is corrected by the entropy of water. And so you put a T as a variable, and then the T temperature, and then you obtain these lines that cross at a certain temperature. But we have not done molecular dynamics simulations
I see.
all
Okay.
the temperature. This is only an approximation, or better, an extrapolation of some punctual calculation.
I see. Okay, I have a few more questions, but unfortunately we won't have time, right? So I will turn off. Thank you.
Okay. Thank you very much. When we are going to move, thank you very much, Frederic, once more time for the very nice presentation. And we are going to move to the next talk of the day, which will be given by Professor Lourdes Vega from Khalifa University, and which will discuss together with us the cooperative effect of self-assembly. We already saw in the presentation of Frederic Thielès the formation of this liposome, I would say more like micelle type structures, and probably we are going to learn more also about similar structures from Lourdes. Lourdes, please. You are mute, maybe?
I am mute. Can you hear me now?
Yeah, we can hear.
Okay.
Perfect.
And can you see the presentation?
Yes. Maybe make it bigger, like in presentation mode.
Yes. One moment. I have two screens, so it always comes in the wrong way.
No problem.
Okay, here we go. So yes, I'm going to build on some of the things we had from the previous talk, but it will be for a very different application, as we will see. Before I start, I want to thank you all for the wonderful organization of this conference. As Frederic said, I know this is very difficult and it's coming out very nicely. So thank you very much for all this work. The work I'm presenting today is part of the work that one of my students, Siva, did on an industrial-based project in which what we tried to put there was some physics and understanding at the molecular level of some of the things they were doing essentially by trial and error. And that's why it's called Understanding the Cooperative Self-Assembly Absorption. The photo you see in the background is Abu Dhabi. And for you to know, I am right now, if I get the pointer, I am right now in the tall building that you see on the front. So why do we work on corrosion inhibitors? Well, this is one of the huge businesses in the world. Globally, corrosion costs have marked $2.5 trillion US, which is 3.4% of the global GDP, as estimated by the National Association of Corrosion Engineers and the World Corrosion Organization. Among these, for the oil and gas industry, the maintenance, the inspection of the facilities, and the replacement of equipment because of failure or because of corrosion are around $1.4 billion US per year. So a way to avoid the corrosion is actually to use corrosion inhibitors, especially in the cases in we have aqueous environments. The global market for these corrosion inhibitors is also huge. 3 years ago, it was $2.7 billion US. And as you can see, it's not only for oil and gas, this is also for power generation, metal processing, pulp and paper, essentially most of the industries. Among this corrosion, the one that is influenced by the effect of CO2 is what is called sweet corrosion. And this is very much encountered in the oil and gas industry, especially in the transportation pipelines. It changes the pH and it causes heavy metal corrosions. What actually happens is if in addition to CO2 you have a saline solution, then you also have the pitting corrosion. This is actually really destroying the materials, and you have one of the photos here. So in addition to pipeline failure and structural damage, it also you also have life-threatening accidents, and you can also have environmental corrosions or pollution that can harm the environment. So this is really a huge problem from the application side. The corrosion inhibitors are working on different ways. So you can have them as barrier inhibitors, or they can be environmental conditioners. They can be in the vapor or liquid phase. They can be, if I can, I want to have the pointer, but I don't get it. Anyway, it doesn't matter. So the ones that we are working on are the mixed absorption corrosion inhibitors, 80% of which are made of organic compounds. How do they work? The absorption mechanism of these corrosion inhibitors is essentially based, the whole performance of these molecules is based on the fact that they are heteroatoms and they form pi electron systems. So usually are amphiphilic molecules in which they have the hydrophobic tail going to the water and they going to the avoiding the surface, and the hydrophilic polar heads. And depending on the type of molecules that you have, they can absorb as a self-assembled monolayer or as a micelle. What you want is to have self-assembled monolayers because these are the ones that will cover the surface. However, you don't have the perfect corrosion inhibitors. So what they do in practice is they inject into the system a formulation. Okay, these corrosion inhibitor formulations are a combination of different types of molecules. Before we started this project, we talked to the company that actually does the formulations, and I tried to understand what they were doing, and they told me they don't know. They say they do this by a trial and error. They know they have different type of molecules that work, but they don't know which one is doing what. So that was a perfect system to really study this from a more fundamental point of view. And what we decided to do is to do molecular simulations to see if we can tailor these organic corrosion inhibitors and relate their structural properties to the macroscopic properties that we are expecting for. So before starting to work, we went into the literature and tried to see what has been done before for these systems. And of course, well, this is much more done experimentally than in modeling. The modeling work is more recent than the experimental work. But what we have observed is that most of the works done were done for a single inhibitor molecule, so one molecule, either in vacuum or in aqueous solutions. These are most of the works done, and even in the ones with water, they were only just one corrosion inhibitor with water. There are few cases and very recent works in which there are more than one corrosion inhibitor molecule. So as I say, most of them one molecule, most of them in vacuum. And we also observed that the simulation times that they were used were very short. So the dynamic of these systems will take time because of the different sizes of the molecules compared to the environment. So it's important to have more or longer simulation times, okay? So then the research questions that we asked ourselves when we started this project was essentially how these corrosion inhibitors protect the metal in the industrial conditions when instead of being in vacuum or just in water, you actually have water, saline water, and then you also have CO2. How can altering the inhibitor functional groups that we have affect the absorption characteristics? And in another way of saying the same question is, can we tailor-make these corrosion inhibitors by changing the functional groups that we have in them? And also when instead of having one corrosion inhibitor, you have several corrosion inhibitors, what is the cooperative effect of these corrosion inhibitors in the system, and how does affect their performance to protect the surface. So then with this, the specific objectives of our work, or the work I'm presenting here today, is to model the absorption of these selected corrosion inhibitors on the metal surface in vacuum in water, and when we also have CO2 on a saturated saline solution. To identify the main functional groups affecting the absorption characteristic of the corrosion inhibitor, to study the inhibitor film formation or the aggregation of them, and the effect of the heterocyclic rings and hydrophobic tails on the absorption of these corrosion inhibitors. For this, we have used classical molecular dynamic simulations, and all the results I'm going to show you today were done at one temperature, 298.15, which is essentially the temperature at which this experiment should happen. The force fields we used were taken from the literature. We didn't refine any force fields. For the inhibitors, we have used the compass force field. For the metal surface, we consider iron 001. The water model we use is the T4PAW because it's the one that has the same level of interactions as the compass that we were using for the inhibitors. And then we have also modeled the sodium chloride and the carbon dioxide. Carbon dioxide also with compass to be at the same level of approximations, and sodium and chlorine from a force field from Fuentes, Alcázar, and Barbosa. Then we have done molecular dynamic simulations in the canonical ensemble, and our simulations were run for between minimum 10 and about, in average, 20 nanoseconds. So as I said, we have done this in a systematic way. So the first type of simulations we did were the simulations of the single inhibitor at different conditions. So the corrosion inhibitors we have picked up is with this idea that I mentioned on trying to identify what is the key effect of the different groups on the molecules. So we have used the TIPA, what we call, okay, so the full chemical names are here with the structure. I will use the short names, okay? So there are two molecules here that have been used, that are used experimentally. One is what we call the HCI TIPA, in which we have the tetraethylene pentamine chain here. We have two rings, heterocyclic rings, and then we have an alkyl, lone alkyl chain. This is the one that in the literature shows to be effective. There are some other studies in which they have used what we call TIPA, which essentially is this part of the HCI TIPA molecule. And we propose to study ITIPA, in which we actually cover the tetraethyl pentamine group, but also the two cyclic groups. In this way, we can isolate the effect of having just TIPA, the cyclic groups, or the effect of the alkyl change on this absorption. We have done this in vacuum on the metal surface that I mentioned before. We have studied this just with water and then with the CO2 saline solution. Once we did the study with only one molecule, then we move into the simulation of the multi-inhibitors in CO2 saline solutions. And then we have also done some formulations that I'm not going to show here because I'm going to focus on the two first parts. So here are the results I'm going to discuss right now. First, I will discuss the single molecules in vacuum, water, and the saline solution with CO2. And then I will move on to the several molecules. So first, I'm going to show you the absorption conformations in vacuum. Of course, this is what is expected. The molecules will absorb on the surface because you have nothing more. There is no more interactions. We have calculated the density profiles to identify which groups of the three molecules. By the way, I will put them always in this order: TIPA, ITIPA, and HC TIPA, to study the effect of the different groups and also the effect of the alkyl chain length on all the properties we are going to see. So as we can see, the TIPA arranges completely planar, trying to touch as many atoms on the surface as possible, and so does the ITIPA. And all of them, they essentially do the same. Here we could quantify with the density profiles where the different atoms on the molecules are. And we also calculated the absorption the absorption energies. And we can see that, of course, because of the size of the molecules, the one that is more heavily absorbed is the HCI TIPA molecule. Then we move on into the case of having water. And as we saw in the previous talk with Frederick also, we can observe here that is a very strong water double absorption layer on top of the iron. And this is actually in agreement with the experimental observations for the water-iron interface. So this is very interesting because we will see that this actually affects the absorption of the corrosion inhibitors that we have. So let's move on to the absorption of TIPA when we have water solutions. So here I'm showing the density profile and the conformation of the TIPA molecule when we have just water, okay? And then here we can see that the TIPA also try to get in contact with the surface. However, the water double layer forces it to be far away from the surface than we didn't have water. Now I'm plotting with the dashed lines what happens with the same molecule when we have the saline solution, okay? So in this case, we can observe that of course is farther away from the surface because now we also have the ions near the surface pushing out the molecule from the surface.
5 minutes.
Yes, this is what we observe when we have the ITPA molecule, very similar, but we can see for the iron nitrogen, we have more or less the same type of as we saw before, and we can now observe where the aromatic groups go onto the surface. In the case of HC-TIPA, we observe something similar. The interesting thing about this case is where the oxygen of the molecule goes, which is the one trying
Sorry to interrupt. Can you share the screen?
Yeah, the screen disappeared.
It disappeared?
Yes.
Oh, I'm seeing it.
Maybe
sorry, when it disappeared?
1 minute ago.
What the heck? Gee, then maybe you did something to me when you say I have no time.
No. I don't know, maybe.
Can you see it now?
It's loading. Yes, now it's visible.
Okay, let me put the full screen. Sorry about this. I didn't realize, by the way, thanks that you told me. One moment.
Yeah.
Okay. So this allowed us to see where the oxygen goes. We didn't have the oxygen in the other two molecules. Okay. Now this is the configurations of the molecules when we have multi-molecules on the system, and that's you can see how they behave. Okay. And then we calculated the absorption energies when we have the saline aqueous solution. And when we compare this with the energies in vacuum, we can see, of course, they are much lower because of the effect of the environment. But interestingly, we see that in this case, the one with the better absorption is the ITPA, that one that doesn't have the alkyl chain. And this is due to the fact that you can see when you look at the right-hand side of the figures, that the HCI-TPA actually forms a micelle. And this is because of the alkyl tail that you have. So it's less effective than the ITPA. Remember, the ITPA is the molecule that has not been studied experimentally, okay? So we further investigated this by calculating the surface coverage, and then we can see that the surface, the molecule that is covering the surface better is ITPA. And we also calculated the radius of gyration, and what you can see from the numbers here, when you compare the XX, YY, and ZZ direction, is the ITPA molecule is stretched, forming this, this film covering the surface. We have also studied the radial dissolution functions to further investigate this. And then it depends if we have just water or if we study the solution with the molecules. But I want to build on the conclusions on the future work. So I hope I have convinced you that we could use, we try to convince also the company paying for this, that we could use these all atom molecular dynamic simulations to separate and quantify the effects of the different atoms and functional groups integrated in the corrosion inhibitor molecules, guiding the ad hoc design of these molecules in different environments. We have seen that when we have single molecules, of course, the energy of absorption is much higher, but the simulations allow us to quantify the relationship between the environment surrounding the molecules and the organic molecules. We have also observed that this strong water double absorption layer influences the whole absorption behavior, and the role of water is key on altering the inhibitor orientation on the surface and then the performance of these molecules. Results from all the simulations we have obtained really guide into using the ITPA molecule as a better corrosion inhibitor than the other two molecules. Work in progress, and I built on the previous one, we are working on using reactive force fields to study the reaction itself, because we didn't do that in the work I presented right now. We are also trying to study the defects of the surface and see also how the corrosion inhibitors will act when the corrosion already happened or it's happening. And also we are working on different corrosion inhibitors formulations. With this, I would like to thank you for your attention. I want to thank the funding that we got from the National Oil Company of Abu Dhabi, and also from the RICH Center, the Research and Innovation Center on CO2 and Hydrogen. And here you have some beautiful pictures of Abu Dhabi, and I'm open now for questions you may have.
Thank you very much, Lourdes. Very nice presentation. And yeah, probably also the view from, by the side, the way remarks, the view from there, the top of the building, it's awesome.
I can show it to you, but then it's too light today.
Yeah. So, yeah, questions? So whoever has questions, please, yeah, unmute yourself. So maybe I start first. So I was wondering, could the reactivity of some of these molecules be studied already at the level of DFT, not to go into extended molecular dynamics simulation to see how they could interact one with another, let's say like small modeling before going to the extensive, of course, real temperature, real conditions?
Excellent question, and the answer is yes, partially. So there are some DFT simulation studies, and we actually have done some. I didn't put them here because they didn't give us much information yet. So yes, we have the information on the reaction of the CO2 molecule with the surface and on the interaction of the corrosion inhibitors with the surface and with CO2. We still didn't find any simulation in which you have DFT simulations in which you have all the ingredients that we have here. But we are also doing this. I didn't mention, we are using LAMPS for the simulations I presented here. We are using VASP for the DFT simulations.
Okay.
Excellent question, thank you.
Thank you. So any further questions?
So I have a question.
Yeah.
You just show us simulations with one molecule, but what will happen if you add more than one molecule? Because I guess that those alkyl chains can self-assembly and...
This is what I show, Juan. This is when I say multi-molecules. Can you see my slide? Yeah, yes. This is the second part of the talk.
Oh, okay.
So in the second part is where I show multiple molecules, all of them have the same concentration.
And then deform these missiles, but okay, yeah. I see.
And then you can see the effect that actually they self-aggregate, and they self-aggregate forming different structures.
Okay, I see now, sorry.
No, yeah, that's fine, thank you. It reinforces what I say, so it's good.
So thank you very much, everybody. You have to move to the next presentation, but thank you once again, Lourdes, for the beautiful talk. So our next presenter is Zhenghe Huang. I'm sorry if I'm pronouncing badly the name, from Shanghai Jiao Tong University. And the topic of today, it will be about single atom catalysis with topological defects. So Zhenghe, please, the microphone is yours.
Yes, I will share my presentation. So, hi everyone. My name is Zhenghe Huang. I'm a PhD student from the Methyl Entropy Materials Lab in Shanghai Jiao Tong University. The topic of my presentation is topological defects involved single atom catalysts for carbon dioxide conversion and oxygen reduction. My presentation will include these parts. In the introduction, we will discuss what is a single atom catalyst and why we focus on the single atom catalyst, why we focus on the defects engineering. Based on the introduction, we will propose a strategy for preparing an efficient catalyst in the section of the experimental proposal. Then, in the result and the discussion, we employed DFT calculations and experimental characterization to analyze the catalytic performance of the as-prepared catalysts for oxygen reduction and carbon dioxide reduction reaction. Besides, for this catalyst, we also studied its practical applications such as zinc air battery. Finally, we will make a conclusion and acknowledgements. As we all know, electrocatalysts play a vital role in energy conversion, such as hydrogen evolution, oxygen reduction, and CO2 reduction. And so far, many kinds of electrocatalysts have been reported. Metal catalysts possess high activity and high conductivity, but it is impossible for large-scale application due to their high prices. Molecular catalysts, such as metal porphyrin, possess high intrinsic activity, but sometimes their poor conductivity will restrict their application. Carbon-based catalysts sometimes lack catalytic activity. So in recent years, single atom catalysts attract many interest. In the single atom catalyst, the metal size can be dispersed in the catalyst support. By combining the advantage of the metal center and the catalyst support, the single atom catalyst can exhibit high efficiency, high selectivity, and structural tunability. Especially the single atom catalyst with metal nitrogen 4 size, like this one, are the most representative single atom catalyst. A high specific surface area of the porous carbon support can guarantee the efficient accessibility of active sites during catalyst. However, the high specific surface area of the porous carbons originates mainly from the topological defects. Yes. A few researchers find topological defective structures such as octagon, heptagon, and some pentagon containing sp2 carbon species can act as active sites. Although such studies are very limited, but this inspired us to develop topological defect-enriched porous carbon for catalyst. So far, many physical methods have been developed for creating topological defects in carbon materials. However, this physical method can only be used for very localized error and can't be used for large-scale preparation. So herein, we developed an effective strategy towards atomically iron dispersed and topological defective porous carbon nanosheets by using azulene-dominated materials as a precursor. Azulene, which possessed 5 and 7 membered carbon ring, was used as a building block to fabricate graphene copper sandwich-like polymer nanosheets. According to the theoretical results and the experimental characterization, we analyzed the activity of this catalyst in oxygen reduction reaction and the carbon dioxide reduction reaction, and also analyze the effects of introducing the topological defects in catalysts. We perform DFT simulation using VASP. The PBE-GGA functional is able to reproduce the graphene type of structures properties quite well. Systems are periodically in X and Y direction. In the Z direction, there are more than 10 I-strain distance between the structures. More than 1 couples have been used. In order to quickly and easily investigate the effects of the defects and the dispersed metal size on catalytic performance, we adopt the Nosgrove method to study the free energy of each species. Besides, we also studied the electrical properties of the catalysts. Firstly, we investigated the catalytic performance of the catalyst for oxygen reduction reaction. In the free energy simulation for oxygen reduction reaction, as shown in this picture, we studied 4 systems. The first system is the graphene system with iron, nitrogen, 4 active sites, and this active site surrounded by only 1, 5, and 7 defects. Similarly, the second system and the third system is a graphene system. With iron, nitrogen, 4 active sites, but the second system is surrounded by 2, 5, and 7 defects. The third system, in the third system, the iron, nitrogen, 4 active site is surrounded by 3, 5, and 7 defects. Besides, we also investigate the graphene system without defects. From the free energy diagram and the table, we can notice that introducing the 5-7 defect can reduce the onset potential to a certain extent. The system of iron nitrogen 4 surrounded by only 1, 5, and 7 defects shows a promising onset potential of 0.72 voltage, while the system without 5-7 defects exhibit an onset potential of 0.63 voltage. However, when we introduce more defects in the systems want to be more active. The differential charge density of this system is also studied. The differential charge density can show the interaction between the surface and the adsorption species. From theoretical results, we can predict the potential application of this catalyst in oxygen reduction. Then we also studied the experimental characterization of oxygen reduction testing. This catalyst also shows high catalytic performance comparable to platinum carbon. As we all know, platinum carbon is an excellent catalyst for oxygen reduction reaction. So we find a catalyst as an alternative to platinum carbon. From the LSV curves, we can notice that the catalyst iron to the MPC shows a better performance. So from the results, the 2D sandwich like nanosheet precursor and iron sites can promote the catalytic performance. Besides, when this catalyst is assembled on the electrode of zinc air battery, the device also shows a promising performance. Compared with other high efficiency iron-based catalysts, our catalyst also shows the best, almost shows the best oxygen reduction reaction catalytic performance. And also compared with other materials, we can also find a promising performance of our catalyst in zinc air battery. In addition to the oxygen reduction reaction, we also want to investigate whether this catalyst can be applied in other catalysis systems, such as a carbon dioxide reduction reaction. Similarly, we firstly studied the free energy simulations for carbon dioxide reduction reaction. We choose 5 different systems. From the free energy diagram and the table, we find a similar pattern with the oxygen reduction reaction simulations. The graphic system with 5 and 7 defects shows bad performance with a free energy gap of 3.48 eV. After introducing the iron nitrogen 4 sites and the free energy of the rate limiting step sharply decreases. By comparing with the system without defects, we can also notice that the system with 5 and 7 defects possess lower free energy gap. Interestingly, when the number of the 5 and 7 defects increases, the free energy will be lower. The system with 3, 5, 7 defects and the iron nitrogen 4 sites shows the lowest free energy of 0.81 eV. Also, the differential charge density and Butter charge analysis are also investigated. The system in the system with 3, 5, and 7 defects, the iron center exhibits minus 1.38 electron transfer, and while in the system without defects, iron atom only shows minus 1.04 electron transfer. The above description reveals a more active iron size in the system with defects. The experimental carbon dioxide reduction reaction testing also shows the as prepared catalyst exhibits promising carbon dioxide reduction reaction catalytic performance. The operando X-ray adsorption spectroscopy indicates ferric iron is a significant active size for carbon dioxide reduction reaction. After reduction to the ferrous iron, the active size, the activity and the selectivity of the catalyst have been observed. The above description is also consistent with the Butter charge analysis.
3 minutes.
Okay. The catalyst has a maximum Faradic efficiency of CO of 95%. This high selectivity surpasses most of iron-based catalysts for carbon dioxide reduction reaction. Now I'd like to make a conclusion for my presentation. First, we propose an effective strategy towards atomically iron dispersed and topologically defective porous carbon nanosheets by using azulene-dominated materials as precursor. So as prepared catalysts exhibit promising performance in oxygen reduction reaction and in zinc air battery. The results shows the potential of this catalyst in practical application. The DFT calculation also reveals a promising onset potential after introducing the 5 and 7 defects in such single atom catalysts. Besides, the catalysts also show high CO selectivity and activity in carbon dioxide reduction reaction electrocatalysis, which is also proved by the free energy calculation and charge analysis. This work paves the way towards high efficient single atom catalysts with rich topological defects for energy conversion. Yes. Finally, I would like to appreciate the experimental support from Dr. Junjie Ding and the simulation guidance from Dr. Diana Trenka, and the nice topic ideas from Prof. Xiaodong Zhuang. I also want to appreciate the conference organizer for giving me the opportunity to make the presentation. Thank you for your attention. Thank you.
Thank you very much, Senke, for the very nice presentation. So now the floor is open for questions. Yeah, I have a question to start. Yes. So if I'm looking at the system, so you introduce this 5-7 defect, does the position of the defect when you have multiple defects, one with respect to another, matter into the output, the results outcome? If your defects are in a specific position one with another, or they are maybe at higher distance one from another, does it make any difference in your output calculation in the results? Does the position of defects one with respect to the other when you have more than one defect matter?
Yes, we studied the different position of the 5 and 7 defects. This system only with 1 5 and 7 defects. We studied different position of the carbon with the 5 and 7 defects, like here or here, just surrounded surrounding the iron nitrogen 4 sites, and to see which system has the lowest free energy. And yes, they show different free energy. But in this presentation, I just only show the best performance.
Okay.
Yes.
So are they stable? I mean, because you propose them for application, are they stable system if you imagine them being used for a long time? So when you include this multiple defect, does it affect in any way their stability or long-term usage? If you would imagine, like you think like cyclability or longer term usage, do you think it will have any effect on their stability, their defects included?
You mean to study the stability of the catalyst?
Yes.
Or
yes.
Yes. From the experimental results, we can see here. Here is the experimental results. We studied the stability of this catalyst for carbon dioxide reduction reaction. Yes, from this graph, we can see the selectivity of the seal is almost stay at 90%, and I think this can show the high stability of this catalyst. Yes, and
okay. Yeah. So, any further questions? If not, I would like to thank again the speaker, and we are going to our next speaker of the day, Professor Eldos Ipe, which will discuss about machine learning modeling in order to understand molecular properties.
Okay.
Yeah. Good morning, everyone. Thank you, Ionut, for the introduction, and thank you to all the organizers for giving me this opportunity to present work. Am I audible?
Yes, everything is sound very well.
Perfect. Okay, I'll share the screen. Can you see the presentation?
Yes, just make it bigger in presentation mode.
Okay, you're on full screen. Is it better?
Well, it's loading yet.
Okay. Oh, sharing is paused. What is this? It's giving a message sharing is paused for some reason. Let me share the full screen and then I'll put the full screen. Okay. How about now?
We can see the screen, yes.
Okay, perfect. It's okay, right?
Yes, it is okay.
Perfect. All right. So my name is Eldos Ipe. I'm from India. So this is I'm an assistant professor in BITS Pilani Dubai campus. So this is one of the international campuses of our Indian Institute, BITS Pilani. And yeah, I'm sitting in Dubai now. So I'm going to talk about machine learning models which are applied to molecular simulations. So I'll show a few examples. Yeah. Okay, you must have heard of machine learning, obviously, because machine learning appears these days in many areas of applications as well as research in, let's say, image processing, in driverless cars, Google, Facebook, everywhere you can see. The good news is that we computational chemists can also do machine learning. So I'm going to show you a few examples. We use this to predict structure property relations. For example, let's say molecules are nothing but structures, and from the structures and patterns, we can predict properties. So I'm going to show you a few examples. And the main advantage of ML models compared to, let's say, QM or MM molecular mechanics calculations is that they are much more faster, and they give an accuracy which is quite close to chemical accuracy. So 1 kilocalorie per mole and so on, or DFT accuracy to say. The outline of the talk, so I'm going to give you a brief introduction about quantum machine learning. So the word quantum machine learning means that we are doing machine learning in quantum chemical systems or molecular mechanics systems, and show you a few examples on the prediction of HOMO and LUMO energies. Then I'll show you some examples on structural relaxation using ML model. And we also did a recent work, some work on virtual screening on docking 3CL proteins. And finally, some scattering kernel predictions on gas surface interaction using ML. Okay, now coming back to the presentations. So what is a representation? So in machine learning or in traditional modeling in DFT or in molecular mechanics, we start with this atomic structure, so 3-dimensional structure. And we cannot use that 3-dimensional structure in machine learning. We have to convert that 3-dimensional data into, let's say, a 1-dimensional array. and that's what we call representation. Now, when we convert this, so in other words, we call features, feature vector. Okay. So when we convert that into a one-dimensional array, there are certain characteristics that we need to ensure. One is that it should be invariant under transformation. For example, let's say a molecule is here, sitting here, and if we spatially transform this molecule, obviously the coordinates will change, but the property doesn't. So any representation that we make on this molecule must be invariant under translation or rotation and so on. It must be unique. No two molecules can have same representation, continuous and differentiable. For example, if you use MD, we need to have first derivative of the potential energy surface, and therefore it should be differentiable. General, it should be able to predict, represent a periodic as well as non-periodic structure, and computationally efficient, and so on. So there are many representations. This is an active area of research in QML. So I'm going to explain few basic. One is Coulomb matrix and then Bagger-Ponz. And there are many modern representations, for example, MBTR, BM, LFC itself, so SOIP, and so on. Okay, how Coulomb matrix works is that, so this is what the definition of a Coulomb matrix. So let's say take a molecule, and we have atoms arranged in space, and Z represents the atomic number. For diagonal elements, we compute the Coulomb matrix elements as 0.5 times Zi power 2.4. For off-diagonal elements, we use this measure. So these are Coulomb measure. And here Ri minus Rj is nothing but the distance between atoms. Now, a Coulomb matrix is the core of most of the representation in quantum machine learning, because these distances, if you take the absolute coordinates, they change when you transform or rotate the molecule, whereas if you take the distances, they do not change if you translate or rotation. So that's satisfying the first criteria of our in the previous page. So once we get a two-dimensional matrix, we can either diagonalize the matrix or flatten it. Okay, flatten means you take the first row, second row, put it next to each other, and so on. So you make a one-dimensional array, and that gives you the representation of the molecule. Okay. So eventually, let's say, for example, if you have a molecule, eventually the representation will be like a one-dimensional array. That's just like this, a one-dimensional array of numbers. Bagger-Ponz is similar to Coulomb matrix. So instead of flattening or diagonalizing, what we do is that we create bags of, let's say, pairs of atoms. For example, all the OO pairs will be in one bag, all the CH pairs will be in another bag, all the CC will be another bag, and we put them all together one by one. So that's Bagger-Ponz. Okay. And there are many other advanced representations, state-of-the-art representation. So if you want to have a look at it, you can just look at the literature. Second part is kernel regression. So how do we do the regression? So a kernel is nothing but a product of representations of two molecules. Here, this is a dot product, and where X and X tilde represents the two representations of any molecule, any two molecules. Once we have the kernel, we can define a relationship between the kernel matrix with the property of the system. So here, this is the kernel matrix, and these are the regression coefficients, and we have the properties. Y1, Y2, Y3 are the properties of the system, and these properties can be anything. So this can be HOMO energy, LUMO energy, E-gap, atomization energy, binding energy, whatever. Okay. So that's the idea. And once we know the, okay, we'll come to training and later. Okay, so these are the regression coefficient, and which can be easily estimated. In addition to this model, this equation, we also add a regularization term, which we can adjust or tune such that we prevent overfitting in the model. Now, what is a kernel? So there are the two different types of kernels that people mostly use, and there are certain criteria which it has to be orthogonal. It should be an orthogonal vector space, and so on. So most commonly used kernels are, first one is Gaussian kernel or radial basis function, which is defined like this. Okay, and the Laplacian kernel. Gaussian kernel measures the L2 norm of the distances between two molecules, whereas Laplacian kernel represents L1 norm. Now, in general, a kernel measures the similarity between two molecules. So kernel is a little bit of relationship between two molecules. So if you take two molecules, if they are similar, then the kernel, the value that you get from the kernel will be higher. And if they are dissimilar, the value that you get from the kernel is very low. So that's the idea. So basically, kernel is something but a similarity measure, a measure of similarity between two molecules. Now let's see how we exploit that feature here. So during learning, so learning versus prediction. In learning, what happens is that we can compute. So let's say we have a data set of, let's say, n molecules. We can compute this kernel matrix like this, K11, K12, K1, etc. And we know the properties of these molecules, Y1, Y2, Y3. The only unknown in this equation is A1, A2, etc., AN, which can be easily computed. Once we know, that's the learning part. Once we know the coefficients, we can do the prediction. So in prediction, what we do is that we have the kernel, we have the coefficients, and then we can find the unknown values over here. Now, how can we apply this to, let's say, a new molecule? So this is equation for a new molecule. So once a new molecule comes in, we compute this kernel vector k nu 1, k nu 2, k nu 3, etc. up to k nu n. So what happens is that so let's say a new molecule is coming in, and we have, let's say, n number of data points, a number of molecules in the data. So we take the new molecule and compare the new molecule with the first molecule, compare the new molecule with the second molecule, compare the new molecule with the third molecule, and so on. And we get a similarity measures of the new molecule with all the existing molecules in the data set. And then we use that information, multiply that, take the dot product with the coefficients, and we get the product, we get the property of the new molecule. So that's the whole idea of this prediction business using ML. So yeah. Right. Okay. Now, how do we validate this model? So obviously we use n-fold cross validations and so on, which is quite standard in this area. So to evaluate the quality of the fit, we use something called learning curves. So this is a typical learning curve. Here we can calculate two types of errors. One is the error in the training data, and another is the error in the testing data. So we split the data set into two, training versus testing. So if you plot the error in both data sets as a function of training data set size, we get these learning curves. Okay. Now from these learning curves, we can define a few things. First is a bias. Bias is the error in the training data. Then generalization error is the error in the testing data. And the variance is basically the difference between them. Now, why is this important? Because if your bias is high, in this case, bias is high and variance is less, which means that your model is not able to predict the training data well, whereas it is reasonably okay with the testing data, which means that your model is of low quality, which means underfitting. Okay. On the other hand, let's say if the bias is low and if the variance is high, in this case, we can see that the model is predicting the data, training data well, versus the testing data is not able to predict. So which means that overfitting. So like, let's say we have a 10 data point and then we put a 10th order polynomial. Obviously it will predict the 10 data points accurately, but if you give another new data into it, it won't be able to predict. So that's the overfitting part here. What we prefer is something like this, where we have low bias and reasonably low variance as well. So this is what we call bias variance trade-off. Okay. Now, coming back to predictions or different calculations. So this is a typical routine calculation that many people do. What we do is that we take a data set. There are a number of curated data sets, for example, GDB7. This is done in GDB7. And we're computing the LUMO, delta E, and HOMO for all these molecules using Coulomb matrix, Bob, using RBF as well as Laplacian. And the most important part here is at this column. So this is a mean absolute error in terms of electron volts. And you can see that most of these models gives an MAE of less than 0.1, which we consider in DFT as kind of acceptable. So LUMO and HOMO of 0.1 is okay for up to DFT simulation. So you can see the kind of accuracy that we get from this model. So there are many works done on equilibrium properties, predicting equilibrium properties. So we thought, okay, why don't we try non-equilibrium structures? For example, since we are dealing with molecular dynamics and so on, we deal with non-equilibrium geometry. So what we did was we took very simple molecules and water, ethane, methane, and so on. And we did random perturbations on these molecules, and we computed the DFT energy, and we asked the question, can ML predict these energies? And the answer is yes. We were able to predict this quite well, and you can see the error, the mean squared error is less than 1 kilocalorie per mole square. And for Bob, whereas for MBTR, this is an advanced representation, we can see the error is less than 0.1 for most of these molecules. Then we ask the question, okay, what should we do with this? Okay, so this is the DFT energy versus the prediction. You can see almost like a 45-degree line. So we thought, okay, can we optimize this structure? So we have the molecule, but we don't have the gradient of energy or forces applied on atom. So we thought, okay, let's do a Monte Carlo. We do simulated annealing. So we all know how it works. So I'll skip this part. So what we do, we start from a high temperature, and then we cool the system down, and we ask the question, does it get to the optimum structure? Yes, indeed. And for most of these molecules, we can see the optimum structure, optimum angle, and bond lengths obtained are quite close to DFT optimized structures. And here is a table which explains the whole comparison. And yeah, okay, I'll skip this. This is the prediction that the resulting forces and the DFT forces of the optimized structure. This also turned out to be quite okay, right? So now let's talk about something which is more relevant. We are living in a pandemic, in the middle of a pandemic. So can we use ML to find a drug for COVID-19? So that we started this work very recently, and then we got some interesting results. So let me give you an overview. SARS-CoV-2 is the virus which causes disease, COVID-19. And so SARS-CoV-2 is a big virus, and it has like many proteins. Obviously, you must have heard about spike proteins, and then there are membranes, and then there's an RNA inside the virus. And then there is the main proteinus, which is the 3CL protein, which plays an important role, very important role in the replication of the virus in the human cell. So once a virus enters the human cell, it replicates, and then 3CL in fact helps the replication of the virus. So the idea is that if we can block the activity of 3CL we can find a therapeutic which can be used for, which can be administered for COVID-19 patient. So this has been a drug target in many studies using, these drugs, for example, lopinavir and ritonavir are under trial, and they're using these drugs for preventing COVID-19. Okay, right. So this is the 3CL protein. You can see that, and if you look closely, here is a binding pocket. So here it is. So somewhere here, and you see this gap over here. So if you can find a drug which binds to this gap, then we have something, right? Now, traditionally, what we do is that in docking protocol, what we do is that we take the protein and we consider that as a rigid molecule, and we take the ligands which are more flexible. So the bonds as well as the bonds are, we can bend the molecule, we can torsion it and so on, and we can rotate it and so on. So the ligands are more flexible, and then they try to we try to dock these ligands, these flexible ligands, into the proteins or binding pockets and so on, and see if it binds properly, as well as it gives reasonably good binding energy. So binding energy is computed using Amorphous, and that's what's being done using docking simulation. So there are typically docking involves like multiple runs of, let's say, genetic algorithm or MMCSA and so on. And then we make sure that we run multiple times, 10 times, 20 times, and 30 times sometimes, to make sure that we get the best binding poses. Okay. So what we thought, okay, let's scan through the drug bank. So this is drug bank contains, let's say, around 8,000 or close to 9,000 molecules, which are either at the experimental stage or at the commercial stage. So we can see if we can, find a drug which binds properly to this 3CL. But the issue is that since it's like 9,000 molecule, if you do docking for all of them, it takes around, let's say, close to 50 to 60 days. So instead of that, can we use machine learning to predict these binding energies? So what we did was we took a fraction of this data set. Let's say out of this 9,000, we took around 2,325% of the data set. And we did docking with a very minimum number of runs. And we predicted the average binding energies. We calculated the average binding energies, and then we trained a machine learning model. So you can see the fit over here. On the x-axis is a binding energy from docking, and then y-axis is the binding energy that we get from the machine learning model. And you can see almost like a 45-degree line, which tells you that, okay, the model is almost okay. But it's not good. It's not the best model, because here in this fit, we have around, the error is around 0.6 kilocalorie per mole. Whereas, so that's okay, but because, you know, the data set that we have contains has an error of around 0.5 kilocalorie per mole. So I don't expect my model to be more accurate than the data set itself. So if the data set has an error of 0.6, obviously 0.5, then my model should have error of more than that. So this is a learning curve, as you can see here. So this is the prediction. This is the out of sample error, or the cross validation error, and it's around close to 0.6, which is okay for our calculation. Now, once we do this, once you do the training, we took the entire data set, the entire drug bank, and then pass so high throughput screening, and then we calculate the binding energies in using the ML model. And by the way, this calculation takes 1 minute, less than 1 minute, maybe 1 to 2 minutes. Whereas if you do the traditional docking, it takes weeks and months. So once we get this, we screen the molecules. Let's say everything below -9 kilocalorie per mole are selected. So we got around 27 drugs, and we shortlisted them, and we redid the docking of those selected candidates. And then we saw that, okay, this docking or the prediction done by ML is in agreement with the docking simulation as well. So it's close to -9, -11, and so on. Now, once we have this -27, we discuss with the biologists and so on, and then we discuss many other criteria of these drugs, and then we selected one out of this one. Oh, by the way, the traditional ritonavir and lopinavir binding energies around -8 and -9. So we got a candidate which is much better than those drugs. Okay, so this is the binding pocket where the drug is getting bound, and then you can see how it's bound. And now what we're doing is that we are just taking this and then doing MD simulations, and then comparing the results and make sure that it binds properly and so on. And then followed by, most likely we'll do the wet lab analysis as well. So yeah, so that's this is the last part. So just one slide. Hope I'm on time.
You are perfectly in time.
Okay, perfect. Okay, so this work is in collaboration with Sylvia, and so what we did was that we asked the question: can ML predict, let's say, scattering kernels in gas wall interaction? So in gas wall interactions, atoms are moving, and then there's incoming velocity, there's outgoing velocity, and they are related, they are correlated. So so typical scattering kernel looks like this on the left hand side. This is from MD, and we use Gaussian mixture model, which is an unsupervised model, and to predict the scattering kernel, and we saw that, okay, there is a good prediction, or the comparison is quite well. And these different colors means that different Gaussians. So Gaussian mixture is nothing but a linear combination of Gaussians. So each color represents one Gaussians. So yeah, so the prediction was quite good, and we also predicted the accommodation coefficient, which was also quite good in terms of its match with MD. Okay, so yeah, I think I finished earlier than expected. So yeah, to conclude. Yeah, so ML is able to predict and correlate the structure property relations with high accuracy and high speed. So that's important. I mean, accuracy is one part. Obviously, accuracy can become a problem if you don't train it properly. But if you train it properly, we can get an accuracy quite close to, let's say, chemical accuracy, up to DFT accuracy and so on. And it's also high speed. I mean, like within fraction of DFT takes like hours, but this takes like fraction of a second and so on. ML model works for non-equilibrium structures as well, and then we use this for high throughput screening to bind 3CL protein. Overall, I would say it's a good model, but should not be considered DFT and MM. We should have that, but this can be used as, let's say, screening of large number of molecules, and then select the candidates and then go for expensive calculations. So yeah, that's it. And thank you for listening. And then if you have any questions, I'll be happy to answer them.
Thank you very much, Eldhos, for a very nice and interesting presentation. So yeah, the floor is open for questions. Maybe yeah, please.
Sorry, if I can. I don't know if you said that and I miss it, but what type of data do you use to train your model? So I guess you did some DFT calculation. Did you use the forces, the energies, the atom position? What exactly did you use? A combination of those?
Right. So mostly we work with, any data which involves the structure. Structure means the three-dimensional structure, the XYZ coordinates of molecules, and the property is valid. Okay. Now, how do we get that property? We use DFT, we use MD, we use force field calculations and everything. So structure versus the property. So if you can get an accurate data set using any model, DFT or anything, it's
okay.
For example, GDB7 is a DFT model, whereas this one, the drug bank is from Autodoc, and the scattering kernel is from using MD. And what else is there? Yeah, this is also DFT. Okay. Yeah.
Okay.
May I ask something? Sorry.
Yes.
May I ask something?
Oh yeah.
Yes. If I understood correctly, because I'm completely new to this machine learning, you basically compare two molecules, let's say with some kind of representation, and from this you have the matrix with the first let's say the answer, and then you get you ask something about some property of new molecules. But for instance, in the case of when you have weak forces like the absorptions, like in protein, all these kind of things, to know the answer of some system to calculate the new ones, this is a very difficult task. So you will depend on how good is the result for this known that you have in your system. So how do you solve this problem? If I am putting correctly the problem.
Well, it's a very valid question. Thank you for the question. The issue in ML is to get the main issue that we face is to get the data out. So, for example, we use DFT for data. No model. If you use any model, any ML model, it will not be more accurate than the DFT data that we use for training. Okay. So, let's say in DFT we use dispersion correction. Obviously the data will be better, and then the prediction will also, ML model will also be better. So it all depends on the data that we use for training. On the other hand, if you use a force field based model, the accuracy that we get from the ML model will also be, can't be more better than the force field itself. So obviously there is a trade-off. As I said, it's not a replacement for traditional calculation, for example, MD or DFT and so on, but it gives a fair bit of idea. It can get as accurate as MD as well as DFT. So it all depends on the data that you use.
Okay, thank you.
Yeah, so Eldhos, you also have some questions in the chat. So one question, what kind of data may be used for machine learning training on a set of solid materials?
I assume it's periodic systems, right?
Yes.
Okay, so the periodic system, there are a number of works which are reported in periodic systems. I haven't worked on periodic system, but I can refer you to Gabor. I forgot his last name, Chesnai or something.
Okay,
maybe if you can send me, if you can send me a mail, I can refer to that person. There are
Gabor,
a number of publications.
From Oxford, I think. Yes,
exactly. So he has worked on mostly SOAP. SOAP representation is from him. So SOAP representation works very well with periodic systems. So there are a number of works which are reported on that. But I work mostly on molecules.
When do you need to go to a more accurate representation?
Right. So in the initial slide, we saw that there are certain criteria that we need to match, and if the criteria are not matching, obviously we need to go for a better representation. But to my understanding, or as far as I understand, even the basic models, for example, Coulomb matrix as well as Bagger bonds, gives a fairly decent models if you train them properly. And so it all depends on the accuracy, and it all depends on what kind of application that we use ML for. And it all depends on the accuracy, obviously. So so for example, this orthodox simulation, we didn't expect an accuracy more than let's say 0.5 kilocalorie per mole. So in that sense, we didn't have to go for. So this is this is not a good fit, but it's reasonably okay, because when we redid the orthodox simulation, we know that the candidates are candidate properties are the properties of the candidates are good. So it all depends on the accuracy that you need.
Yeah. Further question: can you use the Coulomb matrix as an input for the neural network?
Yes, very good question. Okay. Yes and no. Well, it depends on the number of data points that you have. Let's say, for example, the neural network, the issue, the good thing as well as the bad thing is that the complexity of the network. We can expand the neural network in such a way that we can make it as complicated as possible. But that comes with a cost, because it can learn faster, but it will memorize instead of learning. So therefore, we need to check for overfitting. So in order to prevent overfitting, the traditional rule is that we need to have at least 10 times the number of parameters in the model. For example, if you have, let's say, 100 parameters in the model, we need to have 1,000 number of data points. Now, if you take Coulomb matrix, for example, if you take, let's say, 100 atom molecule, the Coulomb matrix will have, let's say, 10,000, at least 10,000 elements or features. Now, if you put that into neural network, we are already talking about more than 10,000 parameters. Now, in order to train that properly, we need to have 10 times of that number of data points. So that is expensive to compute. So that is like, okay, we are doing calculations, DFT calculations on 100,000 molecules to train a simple neural network. So the question is, do we have enough data set? Or should we go for a complicated data set? I mean, what's the purpose? It all depends on the purpose. To my understanding, a simple kernel regression does most of this work quite decent, quite reasonably. So yeah.
Yeah. By the way, because I noticed also when you do this docking, you still need quite a large amount of real calculation. I think there are about 2,500 you mentioned. So that's still something as an amount.
Yeah.
I mentioned that I read recently a paper where they propose a neural network model which needs a little bit less number of points in order to do the calculation. So there is some simplified model. It's mainly applied for experimentalists because, you know, in experiment, if you want to do some machine learning modeling, you have a small amount of data points. And then, of course, you are in trouble because you need this type of points. And there are at least some proposals to be, of course, stated and confirmed, which say, well, you could modify or you could change a little bit your algorithm by using some averages, for example, which could help you still deal with a small data set and not be forced, because that's still expensive, to do a large amount of calculation, which in principle, it is needed for this type of modeling.
Yes, you rightly pointed out, as a misapproach, you can clean the representation. So instead of, let's say, 10,000 long representation, we can shorten it. We can discard the ones which are not playing at all. So that is one approach of cleaning the representation. So yeah, you're right.
Okay, if there are no further questions, I would propose to move to the next speaker. Thank you one more time, Elkos, for the very interesting presentation.
Thank you very much.
So our next guest is Egoi Manzano. I'm sorry if I'm pronouncing badly the name. And we spoke already this morning a couple of times about reactive force field. And I think now for the first time, someone will present and discuss application about reactive force field. So Egoi,
hello.
The microphone is yours.
As you can hear me well?
Yes, yes.
Okay, let's see if I can share my presentation properly. So do you see the presentation properly?
No, it's not shared the screen yet.
It's not shared the screen. Let me, okay. Okay, what about now?
Yeah, now we can see the screen. Yes.
Now?
Should be, maybe you can make it bigger. We can see the screen, but maybe it can be put in.
Sorry to interrupt. Egoy, you are using 2 desktops, right?
Yes.
Oh, now it's perfect.
Now it's fine.
Yeah.
Okay. Okay. So, yeah, well, thank you for the opportunity to present my work here. I'm glad that we talk a little bit, or we mention at least the reactive force fields in previous presentations. And what I will present now is our studies using these reactive force fields to study dissolution of minerals and how we apply it to study cement hydration. So I understand that cement is not a very common material in this kind of forums in condensed matter physics, but it's clear that it's an important material. So it's used worldwide for everything. Cement is everywhere. We use it for houses, any type of building, infrastructures, and so on. So it's also a very cheap material, and those are all advantages. But the negative side is the huge environmental impact of this material, of cement. So this is associated to the production of the material itself. And well, even if it may not be the most destructive material on Earth, as they said in the Guardian newspaper, it's true that the CO2 emissions associated to cement are very high. So in our research, what we want to do is to try to understand the material, because there is little understanding about this material from the atomistic point of view. It has been classically, it has been an engineering material, and they didn't pay much attention to what was going on at the atomic scale. So we want to try to make relationships between structure and properties to improve the performance of cement, and improving the performance, so somehow try to reduce the CO2 emissions by, for instance, using less cement, if we can improve the properties. So what is cement? So cement is the gray powder that they sell we can find here in these bags. It has gypsum, and it has organic chemical components to control a little bit the properties, but essentially it's made of 2 crystalline phases that are called C3S and C2S. In cement chemistry, the nomenclature is a bit funny. So C is not carbon and S is not sulfur. C, they use it for calcium oxide, and S for silicon dioxide. So in principle, what we have are 2 artificial minerals, tricalcium silicate and dicalcium silicate. You can see here in the bottom, you can see the structure of dicalcium silicate, which is actually similar to natural materials. This would be like artificial minerals. And this is actually a very common structure for dicalcium silicate that is the same as olivine, so magnesium silicate that appears in nature. So it will be the equivalent with calcium. So we have crystals that look like minerals, so we can study them as for any other material, even if sometimes cement looks like a weird material. And in this presentation, I will show results on the hydration of these cementitious materials using DFT and reactive force fields. So for DFT, our simulations are quite standard, so I'm not going to enter into details. For RSEF, we already mentioned them, or other speakers already mentioned them in their presentations. I will give a very brief description. So RSEF is like any other mineral, like any other force field, an empirical force field. And it has, as you can see here in blue, has a short range term for bonds, angles, and so on. Some non-bonding terms for van der Waals interaction and Coulombic interactions, and then some energy terms for specific interactions like hydrogen bonds, for instance. So the peculiarity is that all these bonding terms depend on the bond order. So at each step of a molecular dynamics simulation, the bond order is computed, and it's part of the order goes to 0. The energy terms are 0, and essentially that's a bond breaking step. And the opposite, you bond atoms and then it's different from 0. It uses also variable atomic charges, so use at each step of the simulation of the molecular dynamics simulation as well. The charges of the atoms are computed with the charge equilibration method. And then the last peculiarity is that it uses unique atom types. So, for instance, an oxygen atom is the same type of atom, even if it belongs to a water molecule or if it belongs to a silicate framework. It doesn't matter. So that allows smooth transition in these chemical reactions. So the problem that I will show in this presentation is, well, I would show two. The first one is the difference between beta dicalcium silicate and gamma dicalcium silicate. So these are two polymorphs that may appear in cement. One that we want because it has a fast dissolution, and we want that for construction purposes. But the bad part about the beta form is that the synthesis temperature is like 300 degrees higher than the gamma polymorph. So higher temperatures implies higher fuel consumption and more CO2 emissions. So we would like to have the gamma polymorph, but with higher dissolution rate, faster dissolution. And you can see here an atomic representation of both of them. So it's quite similar. I mean, different polymorphs, clearly, but they are not, at the first glance, there are not big difference between them that could imply this difference in dissolution rates. So the first thing that we did was using DFT, try to study the surface energies. So our idea was that the most stable polymorph should have lower surface energies and therefore more stable, less reactivity. And we actually found the opposite. You can see here but we did it for with DFT, with PBE and double zeta polarized basis set using Siesta. And we did it for the low index surfaces of the two polymorphs. And you can see here the surface energies, the lowest and highest for beta and lowest and highest for gamma. And you can see that the surface energies for the beta polymorph are lower. So that's opposite to what we expected. Then we decided, okay, then maybe it's not surface energy, it's the reaction of water with the surface itself, what is different. And what we did was select different points at the surface of these two materials. We took, let me go back, we took two surfaces because with DFT it was quite expensive to explore all of them. So we took two of them, the lowest energy surfaces. And we took some points and used again the same method, DFT, with the PBE and double zeta polarized basic set, and an elastic band methodology to study this chemical reaction of water with the surface of these polymers. And we found that the process was similar in both cases. There was, here you can see the energy as a function of the reaction coordinate. And what we saw is that there were usually three energy barriers. The first one associated to the rotation of the water, because maybe our first initial guess for the position of the water molecule wasn't perfect. So it was a little bit of rotation to get the optimal position for the reaction. The reaction itself was the second energy barrier. And in the reaction, essentially what happens is that water splits and forms two OH groups in the surface. And then there was a tiny third energy barrier of the diffusion of these two OH groups to find the optimal position. But the interesting thing are the energies that we have here. We found that essentially the energy barriers of dissociation, that were the highest ones, were more or less equal in both polymorphs. And for the gamma one, that is the slow reactive one, we even found cases in which the energy barrier was zero, so spontaneous reaction without energy barrier. So again, this is opposite to the macroscopic observation. And then we decided to start with RSEF-GEFES because our first maybe the selected points for the chemical reactions weren't as good as we expected. We chose 9 by hand, let's say. So we wanted to have a better initial guess. And what we did was these water absorption energy maps. So in the surface of the material, what we do is place a water molecule in different positions. We do one simulation for each position in kind of a fine grid of positions in the surface. And for each position in the surface, we also test several initial configurations of the water molecule. So at the end, we have for the surface, we have like 9,000 simulations more or less, and we can reconstruct, taking the most stable results, we can reconstruct this type of absorption energy maps. And the color is giving us the places in which the absorption energy is positive, so favorable and negative, so favorable. So we found that, as you can see from the maps, the gamma polymorph actually has the most stable places for water absorption, and even here in these specific spots, there was chemisorption automatically without any energy barrier, as we saw with DFT. But the difference is that in the gamma, the low reactive polymorph, there are few spots in which the reaction is very favorable, while in beta, it's less favorable, the absorption and the chemisorption, but there are more places in the surface in which the reaction can take place. So we made an estimation of 2 sites per nanometer square for the gamma and 5 for the beta. So we thought that this was the real reason behind the difference in reactivity, that even if reactions themselves are more favorable for gamma, they were less sites, and then macroscopic dissolution was less favorable at the end. So we can test, that doing molecular dynamics at room temperature, and we put like 10 water molecules per nanometer square in contact with the beta and gamma surfaces in blue and orange. And we can track, doing molecular dynamics during 2 nanoseconds, the amount of reactions that took place per nanometer square, sorry. So we can see that in the beginning, in both surfaces, the reactions are very fast, but then soon after the beginning, we saturate the reactive points in gamma, while in beta, reactions keep going on. So this corroborates a little bit our conclusion, and we think that the gamma polymorph is less reactive because there are less reactive points in the surface. So we want to go a little bit farther, but before doing bigger systems, we wanted some sort of easy test material to see the capabilities of RSEF-GEFES. And we chose calcium oxide because the water dissociation in calcium oxide is a very simple process, very similar to the one that we have for this belite. So water splits into 2 OH groups, and there is no energy barrier for this splitting. So it's a very hydrophilic material, and this reaction takes place without energy barrier, and that's results from DFT from RSEF-GEFES. And not only our DFT, also DFT from the literature. So we can do the same as before. We can place, in this case, 16 water molecules per nanometer square, which would be like 1 monolayer of water at the 001 surface of calcium oxide, and room temperature, and run the simulation, in this case, half a nanosecond. There is a very fast dissociation in the beginning, and then as the reaction points start to be saturated, so the reaction goes down, the reaction rate. And the very interesting thing that we found here is that there was a topochemical reaction in the surface. So as you can see, the last step before the topochemical reaction, so around here, and here would be after the topochemical reaction. So in this case, water has reacted, forming OH groups in the surface, but we still have kind of the cubic structure of calcium oxide. And suddenly, at some point, there is this change in which the layer of calcium goes a little bit up, and the OH groups turn from being up to being down, forming this type of different layer that actually corresponds to an hexagonal brucite-like structure, which is the structure that takes calcium hydroxide. So it's a topochemical reaction that takes place in the surface. we wanted to go further and do a real dissolution simulation. So as you can see here, we have a slab of calcium oxide of 14 nanometer squares with 5 nanometer thick water in the top of it. And we can actually run 2 nanoseconds of simulations. We can go further, but for what we wanted. And as you can see, we can actually see the dissolution of the material itself. You can see how reactions took place in the surface, and some of the calcium atoms even start to go to the pore solution. So we can see dissolution at the atomic scale, and for us, this was a very nice result. But can we quantify something from here? And well, the answer is yes, of course. We can do this at different temperatures, and if we monitor the number of water molecules reacting in the surface as a function of time at different temperatures, from these slopes we can obtain the dissolution rates essentially, and if we do this at different temperatures, we can use a Arrhenius equation to do the Arrhenius plot of the logarithm of the rates as a function of the reciprocal temperature, and from the fit we obtain the macroscopic activation energy of the material. And our macroscopic activation energies are, well, our simulation energies are in very good with the macroscopic results from experiments, both from the activation energy and from for the pre-exponential factor. So we were very happy of being able from atomistic simulation to obtain macroscopic activation energies. And that was all. Just as a summary, we can say that RSEF can give us information beyond DFT. Of course, we have to be careful because this is an empirical potential, and we must be very sure of what we are doing and the quality of our force field. But in principle, there is a lot of information that we can obtain. In the case of belite, we were able to identify why is the reason, or what we think is the reason behind the low reactivity of the gamma polymorph, and is the amount of reactive sites in the surface. Even if the reactions are more favorable in gamma, there are less sites for reaction. And in the case of calcium oxide, we were able to see a very nice topochemical reaction when we were working with a water monolayer, and when we were working with bulk water, we were able to obtain the macroscopic activation energy, and in very good agreement with experiments. So we hope that we can now apply this type of methodology to study cementitious materials and get interesting information for industry and try to improve the performance of the material somehow. So thank you very much. That was all from my side.
Okay, thank you very much, Igor. Very, very interesting presentation. So the floor is now open for discussion. If there are questions.
Yeah, I have a short question.
Please.
It's on the, at some point you showed this figure with the absorption sites of the, yes, I was already, this one. Yeah. You mentioned that you did molecular dynamics calculations to compute the absorption, or was the energy minimizations, or what? How did you actually compute those?
Yeah, in this case, it was energy minimization. So we were putting one water molecule in different positions and doing the energy minimization, yes. And then molecular dynamics was in this.
Okay. Yes, okay, thanks.
One more question. Would you imagine using, for example, Monte Carlo approach to study, for example, better the incorporation of water into the cement, into the bulk of the cement, rather than waiting? Would it be an idea to use a Monte Carlo approach to look better at the presence of water into the bulk of the cement? Because in Monte Carlo,
canonical Monte Carlo.
Yes.
Yes, and there are groups that have studied that. Yeah, you can definitely do this. The thing is that with RSEF, using Monte Carlo is a bit difficult, because if you do canonical Monte Carlo and then the water molecule reacts, then do the removal movement of the canonical is a bit messy. And as far as I know, nobody has implemented it so far, but you can do it.
No, there are some Grand Canonical protocol, I think, implemented in ADF, if I'm not wrong, SEM code from Amsterdam. I'm not sure if LAMP says it. I'm not familiar with the code, but it is present in SEM package from Amsterdam.
LAMPs can do Grand Canonical Monte Carlo and with RSEF-GEFES, but then you start having conflicts then after reactions. ADF, I don't have access to it, so I have never tested, so I don't know the capability.
Okay. And here you could actually extend to other cements. For example, I know one popular cement is mined, calcium, aluminium, oxygen, if I'm not wrong. So that would essentially, which is quite interesting from many actually points of view, not only it is a cement, but it's a cement with some smart properties. So that would be actually interesting to do such type of modeling when you expand from, let's say, standard cement, let's say so.
Yes. And we have done it. For instance, we have a work on different cements that are based only on aluminum and silicon that we used to call, in the cement community, they call them geopolymers, but they are actually like sort of amorphous zeolite, something like that. And we have already applied RSEF to that kind of systems as well, to study a little bit the formation of these amorphous calcium silicate frameworks with RSEF. So very related to the first talk that we had in this morning, yes.
Yeah. Okay, so if there are other further questions? If not, I would like to thank one more time to the speaker. Thank you very much. And then invite the next speaker, Koen Heijmans, to discuss about thermal energy storage in materials.
Yes, thank you. Oh, wait, for the sharing. No, now I can share. Yeah.
Yeah.
One recommendation, if you have our application open on the desktop, it's always good to close them because otherwise there can be problems with the connection and we might lose you from time to time. That's ideal to be able to hear.
Okay, can you see my presentation?
Yes, it's visible.
Okay, good. Okay, welcome everyone. I'm Koen Heijmans. I'm a PhD student at the Technical University of Eindhoven. And thank you for the opportunity to present some work at this conference. So what we're doing in Eindhoven is we're using a molecular scale modeling to study dope thermochemical energy storage materials and see how we can improve them based on knowledge gained from this molecular or microscale modeling. So first I would like to explain a bit on what's actually the concept or the idea of thermochemical heat storage. So in this idea, we want to store heat in the chemical reactions between two different elements. And for this, we're using mainly salts, and in our case, magnesium chloride and calcium chloride hydrates. So the idea is that that you have a dehydrated salt. Okay, you see my mouse pointer screen? Okay.
Yes, it's visible.
Okay, so that you have a dehydrated salt, which is very hygroscopic. And then if you put it in contact with water vapor, it will react, and via this exothermic reaction, a lot of heat is released, and we can use this heat, for example, for domestic heating. Then at some point, the salt is completely hydrated, and actually your storage system is discharged. And then in times where we have enough surplus energy from something else, for example, in summer from solar collectors, we can dehydrate the salt again and do the cycle up again and again. So in this way, you can store the heat of the summer and, for example, released in the winter. The advantage of such a system is that you don't have any heat loss over the storage time. And the advantage of magnesium chloride and calcium chloride hydrates is that you have multiple hydration levels, which is also again then reflected in a higher energy density. these salts are also widely available, and that's reflected in the price. However, there are also some challenges to these salts. For example, the stability and cyclability. So we want to use the material over and over again. The dehydration and hydration rate. So we want to have fast kinetics and high power output. So these are actually important that they are high, which is for most salts still a problem. Deliquescence is something that could occur if we overhydrate the salt actually, and then it will completely dissolve. Melting of a salt, so if we go to too high temperature, and this is mainly the case for calcium chloride hydrates. For the higher hydrates, we melt the salt. And hydrolysis, which mainly occurs for magnesium chloride hydrates, that happens when we dry it at a too high temperature, and then at some point hydrogen chloride can be formed, which is actually a thing you of course want to avoid because it's highly toxic and corrosive. So there are actually some possible solutions proposed to improve these salts, and that's actually the combination of these salts. So there are already studies that show that a combination, a compound of magnesium and calcium chloride have a higher resistance to hydrogen chloride than the two separate salts in pure form. And also it shows, some studies show that if you incorporate for example, calcium into a magnesium crystal, it's improving the water dissociation, especially near the surface. However, there are still a lot of properties unknown for these combined salts. For example, some of we listed here. So what's the energy density of this combined salt? What's actually really the stability of such a crystal? The diffusion through salt? Thermal conductivity, hydration and dehydration rates, etc. And these are actually things we want to study with molecular modeling. And we do that at two different levels. So on electronic level T with DFT. On this level, we try to discover how these crystals of combined salts actually looks like, what the stability of these crystals is. And we did some chemical bonding analysis on this crystal to say something about hydrolysis resistance. And then we take it one step bigger to an atomic level with reactive force field, where we try to model the things like diffusion and dehydration rates. So first, let's look at how these crystals actually look like. So we did actually two approaches. One approach was to take the experimentally known crystal structures of all the different hydrates of pure magnesium and pure calcium, and then we simply start swapping magnesium with calcium, and also the other way around, calcium with magnesium. And so in this way we had some kind of basis set spanning the entire range of different rates between magnesium and calcium in the crystals. And then next to that we also used USPEC, which is a genetic algorithm used to predict new structures. And then in each generation it takes actually the best, the most stable structures of that generation, and the code does permutations or mixed combination of these crystals to come up with a new crystal, which is hopefully more stable, and in that way you zoom into probably the most stable structures. And then we analyze these structures by using the convex hull. So what is the convex hull? The convex hull is actually a measure to qualify the stability of such a crystal. For example, if you have a pure component A and a pure component B, and then you have a mixture of AB, from which you have the compute energy with DFT, and then the energy of the convex hull is actually the this energy minus the energy of the pure component A times its fraction, and the same for B. And then we have some leftover energy, and this leftover energy says something about stability. Now, when this leftover energy is below 0, you can say, okay, it's more stable than the pure components, and when it's above 0, it's less stable. And then the convex hull is actually the surface you get from the most stable structures. So we did this for all these manually doped structures, and also for the most promising USPEC generated structures with a genetic algorithm. And then this is the result. So all the blue points are actually for anhydrous, red is dihydrous, and black is the tetrahydrous structures. And then the dots are from the genetic algorithm, and the symbols like the squares and the circles are from the manually doped structures. The thing we see immediately is that all the new explored structures are actually above 0, so that means that they are less stable in combination than in the pure separated form of the crystals. However, this energy difference, if we look at the most promising structures, is very low, which means that, which could indicate that they are actually feasible, especially if we look at these two green points, which are actually experimentally observed tachyhydrate structures. Then we can also extract the water out, and we get some kind of 3D convex hull. And you can see for example, also the heat of formation, which is released by hydrating these salts. And then the results of these we can compare with the experimental results, and these are actually also really close to the heat of formation for these salts. Then from these most promising structures, so which are indicated here by the dashed line, we did a chemical bonding analysis for which we used the DDEC6 approach to say something about the strength of the bond and also the charges on the atoms. Next to that, we also did a Bader topological analysis. And from that, we also get something on the strength of the bond, but also the type of bond. And then here's an example of the Bader topological analysis, where there are two sections through the crystals, to the doped crystals are given. And then from these electronic density distribution in this section, you can say something about the type of bond. For example, here we have a oxygen-hydrogen bond. And then based on the potential energy density and the kinetic energy density, at that point you can say something about, okay, is the bond covalent or is it ionic interactions? Then if we take a look at these interactions, and specifically in the hydrogen chlorine interaction, because this is an interesting interaction to say something about why does this hydrogen chlorine is formed in magnesium chloride and not in calcium chloride, and can we say something about it when we start doping? So for this interaction, we actually looked in what happens with this interaction based on the environment, if it's in a magnesium or a calcium environment. Then first thing we observe from this chemical bonding analysis is that the chloride is stronger bonded to calcium than magnesium, and also the water in a calcium environment is less polar than in a magnesium environment. And then if we plot the charge difference between the hydrogen and chloride, we see that at the point that the oxygen is bonded to magnesium, the charge difference increases between hydrogen and chloride, and when it's bonded to calcium, we see it's decreasing. At the same time, we see that if the chlorine is bonded to calcium, then the bond order between hydrogen and chloride increases. However, as we already said before, the bond between chloride and calcium also increases, which makes this this change relatively neglectable. Then these all these data we got from DFT, we actually took it to study with the reactive force field. And reactive force field is actually, if we look at the computational scales, it's trying to bridge the gap between QM and classical molecular dynamics. And in the previous presentation was already explained a bit on RSEF, so I'll keep this very short. But the main advantage of RSEF is that you can model bond breaking and formation compared to the non-reactive force fields. And then if you train such a force field, for example, you can model things like diffusion and see what happens within the crystals and how does the water, for example, translate. And the first thing we did for these dope salts actually is to look at the dehydration. So here we have plotted the blue line. Sorry?
5 minutes.
Okay. The blue line is the dehydration for pure magnesium. Then we have the red line, which is dehydration for pure calcium. However, if we have magnesium with only 10% of calcium, the dehydration of the magnesium already increases significantly, which is probably caused because of the larger calcium atoms, which can cause some steric effects. Then we tried to do some grand canonical Monte Carlo simulations with the salts. So in these simulations, actually we take a magnesium chloride slab and we try to insert water molecules into it and see if it starts hydrating, and this water molecule is then fixed to this box by with an imaginary reservoir at fixed temperature and chemical potential. However, before we started doing this, we checked our force field, how it could, if it could recreate the VLE or the vapor-liquid equilibrium of water. And here you see it's actually quite good in agreement with experimental results and also with the TIP4P, which is a non-reactive force field considering water. And then here you also see from these images how this loading of such a magnesium chloride looks like. And then this is actually still ongoing work, but you see that we started with, for example, with different crystals. We have the tetrahydride, the dihydrate, and the anhydrous structures, and we started loading them at 300, 400, and 500 Kelvin. And then you see that 300 Kelvin, all the different hydrates go to the tetrahydride at some point, converts to these. At 400 Kelvin, they convert to the dihydrate, and at 500 Kelvin to the monohydrate, which is actually also quite nice in agreement with experimental results. Then another thing we did is actually did something similar as also in the previous presentation, is that we took a magnesium chloride crystal, and then actually instead of taking a completely dry crystal, we inserted at 3 points a water molecule, and then see what is the how likely is it to be a new water molecule accepted in this crystal. And then you see that at the locations where there was already a water molecule, it's much more likely to be accepted than in the other, and the absorption energy is also higher, and it's much more likely to be accepted than in the other points, which could indicate that for practical reasons, you should not try the heat storage completely, because then if you start hydrating it again, so some leftover water molecules could really boost the performance of the system. And some conclusions. So we saw from the convex hull that we saw from the chemical bonding analysis that there is some effect on stability for the different hydrates. However, for the higher hydrates, this effect becomes lower, and the difference in stability between the doped and the pure becomes lower. And there is also a trend for a reduced hydrogen chloride interactions in a calcium environment. Furthermore, adding calcium to the magnesium chloride crystal increases dehydration. And first results also show that this Grand Canonical Monte Carlo in combination with RSEF could be used to estimate loadings of this new salts. And by that, I would like to thank you for listening, and if there are any questions,
Thank you, Koen. Thank you for the very nice presentation. The floor is now open for discussions. So if there are questions?
Yeah, I have one.
Yeah.
I like very much the presentation because very different systems, very different applications, but we do kind of we take similar approaches. So it's very nice. Yeah. And one question is about the force field itself. Did you parameterize the interactions, or they are taken from literature?
No, for example, the magnesium chloride force field we have, it was already trained and parameterized in our group. Then the water interaction on itself is I parameterized a bit further to improve the performance for this VLE. And at the moment, we're also working on the calcium chloride and a mixed force field for those.
It will be very interesting for me as well to have chloride together with silicates and calcium to study things like corrosion as well. And the second question is in slide 14, I think it was.
Yes. This one.
Yeah, in 14, there was some snapshots of the simulation, and it looks like the material, the bulk material was, yes, in this one, it looked like the bulk material is completely destroyed when you absorb water inside. There's an amorphization. There are evidences of that happening from experimental point of view when the water is absorbed.
As far as I know, yeah, this is not experimentally. It's not studied or not. I didn't find it anywhere. But indeed, by hydration of this water, it destroys more or less at least the surface of the crystal. And of course, this is still a very small slab. And what I would expect that at some point, if the water content is high enough, it would again nucleate in a different crystal form of the higher hydrates than in that form. Of course, that's with molecular dynamics. It's on such a long time scale that we probably would not observe it in these simulations.
Thank you.
Yeah. Are there further questions? If not, I would like to thank one more time the speaker. Thank you. And when we go to the last talk of today, it will be given by Sidong Tu from St. Louis University, United States. And it will deal with self-assembly of battle brushes. And we'll likely go now to a higher level of modeling, where we look at coarse grain modeling. So,
can you hear me?
Yes.
Okay, I'll share the screen. Sorry. Okay, can you see the screen?
Yeah, it's perfect.
Okay, thank you. So thank you all. And I'm Sidong Tu. I'm a PhD student from Clemson University. And today my topic is about the self-assembling of bottle brushes with polyfluoropolyester side chains. And this would be focused on the molecular organization at this era and the thermoplastic interface. So first, I would like to have a brief introduction about bottle brushes. So bottle brushes is polymers with long backbone and densely grafted with these side chains. And this special structure of bottle brushes has bring it special properties. This densely grafted side chains has provided steric repulsion, thus somehow stretched this backbone, and it increased the spatial density of the chain entanglement. And the structure of the bottle brush could be tailored easily, so they will have a lot of kind of bottle brush. Another way is like those kind of chemical component could be changed easily by synthesis of the bottle brushes. So it is a wide application from phototoxic material and from like the interface part. So here is one of the example of bottle brushes with different type of the side chains, PBA and PEO. They have the oil affinity part and the water affinity part shows that this water and oil interface. And in this experiment, people has watched the stretch out of the bottle brushes. Also in our experiment for single chain at this water and oil interface, we observe the similar stretch effects of this backbone. So next, I would like to introduce our experiment findings. Our collaborator found that with small amount of addition of this PFP-based polymer macrolate bottle brushes, the thermoplastic like nano 6 and PMMA, they are all for basic could be increased significantly. Previously, the well-known material for this oil repulsive would be this Teflon, and we can see that with very 0.5 to 5 weight percentage of these bottle brushes, we could see a significantly increase of this thermoplastic. And also for this TF images for the nano bottle brushes, adding thermoplastics, we see that there are larger domains in this nano 6 case than the PMMA case. And reflecting in the oil for base case, the nylon case has higher oil for basic repulsive, sorry. And previously, people used this perfluoroalkyls for the oil repulsive material. However, it is already phasing out because the bioaccumulation and it is also toxic. In our simulation, we use PFP. It is environment friendly and it is also chemical inert. So for our research, we plan to develop suitable modeling approach for this bottle brush and the small plastic system and trying to find their features. So first, I would like to introduce the co-screening of our models. So based on the chemical structure of the bottle brushes in experiment, we started our models with co-screenings. Each of the beads will represent 3 water molecules in our simulations, and the structure of the bottle brush could be controlled by 3 parameters: the length of the backbone, the length of the side chain, the grafting densities, and the beads are connected with the harmonic bond potentials. And in this research, length is used. So I would like to have a brief introduction of the dissipative particle dynamics. So it's a little similar with the MD simulation. It's also governed by the Newton's law, but there would be strict but they use different thermostatic and also they have different potentials in the DPT simulations for computational efficiency. Instead of the traditional Lennard-Jones potential or other force field, we use softer repulsion parameters. That means within the cutoff distance, the constant force would be calculated just linear with this distance, and I'll just use the mouse instead of the laser. So for the same type of the beads, the softer repulsion parameters could be calculated by the inverse of the compressibility. Here, the NM is the degree of co-screening and the alpha is constant. So as I previously introduced here, each of the beads represents 3 water molecules, and the density of the simulation system is 3. We could calculate it that for the same type of the beads, the softer repulsion parameter between the same beads would be 78. And also with this co-screening system, we could get the length of the each bead that is also our cutoff distance and also the time steps. Meanwhile, for the different thermostatic method I mentioned previously, we also need to meet the fluctuation dissipation relation for the dissipative force and the random force. So for DPD, there is a lot of advantages. The most important one is it provides high computational efficiencies, and it also gives like algorithmic simplicity, and the momentum is conserved. However, this is also bring problems like the unphysical crossing of the chains, because we're using the softer repulsion, as I mentioned in previous case. Sometimes it happens as here, we might see unphysically bond crossing during the simulation process. To avoid this part, we use a modified segment repulsion parameters. That means we add additional bonds between the bonds itself. Here, we use the midpoint of the point, and also assign the forces with relation forces proportion to the distance. So we tested this MSRP DP with the linear polymers in good theta and pro solvent, and find the scaling relation is in good agreement with previous theory. So next, we would want to discuss about the softer repulsion parameters. Previously, we calculated that one within same type of beads, but for different types of beads, this softer repulsion parameters could be calculated with Flory-Huggins parameters, and this AI relation between AIJs to the Flory-Huggins parameters could be related with this formula and shows in previous simulation results. And we also tested this one with MSRP, shows in the red dots in this plot, and it also shows good linear fitting. And for computational efficiency in these simulations, we use single bits instead of the long chains for the thermoplastic part. So for our previous simulations, we find that if we use different lengths of the chains, they have the phase separation will happen at different AIJs. So for a good ideal situation, we should use the long chains as 8, but since for the computational efficiency, we use 0 here, that means we have to increase the AIJs for the softer repulsion parameters. And so for these studies, we first calculated the surface tension based on the cohesive energy, and then we used the Tagami-Hefford equation, calculate the Flory-Huggins parameters based on the surface tension, and then we calculated the AIJ and increased them with the point where the AIJ equals to 89, where the phase separations definitely happened, and this phenomenon is observed in the experiment. And then we use corresponding AIJs, which follows the relation of this surface tension. So we first verify our simulations with single bottle brushes in solutions. So here we compute the radiance of duration of the backbone of bottle brushes. We first use a model which has a servophobic backbone, and we change the side chains from length from 1 to 20, and also we change the affinity between side chains to the solvent from high affinity to low affinity. Otherwise, it could also say that from a high solubility to a low solubility. So from the data, we find that with the increase of the length of the side chain, we observe that the RG of the backbone increases. As mentioned in the first slides, the steric repulsion of the side chains could be stress the backbone. So the RG is increased. Another one, we observe a transition from the random coil structure to a global structure, and the transition point is somehow happened at this theta condition, and this results are in good agreement with the previous Cold-Screen MD results and verified our bottle brushes. And next we also tested the bottle brushes, which is in our experiment conditions. The bottle brush has a solvophilic backbone and has a and change the affinity between the side chain to the solvent. And we also observed the similar results as this case. And then we characterize the system with the shape anisotropy. The shape anisotropy is calculated from the radiant duration tensor, and it's a value between 0 and 1. And when it is equals to 0, that means this the items has a high symmetric shape like sphere or cubic. When it is equals to 1, that would be linear, and when equals to 0.25 means it is planar. So for the polymer, for linear polymers, previous case has shown that the shape anisotropy value for a linear polymer in good solvent would around 0.41 to 0.45, and in theta solvent is like 0.39. And here, this is the calculation for the one single bottle brush. We see that when the side chain has high affinity with this solvent, the shape anisotropy value is around that one in good solvent, means it has this random coil structure. Then at this low affinity, it goes values very close to 0, means it goes to these global structures and has high symmetric structures. And then we also see this transition point as mentioned previously. And the next would go to the cases where we add multiple bottle brushes in the system. We first make the systems with multiple bottle brushes and the thermoplastics, which is represented as the single bits, and the softer repulsion parameters is used with the previous case following the relation as the surface tension. And here we use just 5% of the bottle brushes as shown in the experiment. And then we observe the aggregation of the bottle brushes in PMMA and nylon 6, and we find that in nylon 6 they have a faster aggregation in the thermoplastic, and after long enough time they finally form one cluster because they want trying to minimize the surface tension. And then we take this one cluster to the cases where we will look at how they works with this interface. We add this air interface with very high softer repulsion parameters, which means all of the species has very low affinity with this air, because air has very low mobility, and in this cases nothing is react with this air. So all of the species will have a very high repulsion parameters with this air. But since we have different surface tension for air and PMMA and air and nylon, there are also values differences. So we first calculated the shape anisotropy, but this time is for the whole clusters. And for this part, we could see that when we started from the time where the cluster starting to attach this interface. At this starting point, the cluster is still in this polymer thermoplastic, so it still keep this high symmetric shape, and the K-square values is close to 0. But when it trying to migrate to this interface, we see the K-square values increase very fast, and finally goes to the values close to 0.25, which I introduced previously, the values for shape anisotropy at this planar. And for these two different cases, for the nylon cases, it has a much faster migration speed than the PMMA shows in this plot. It has a higher deep slope than the PMMA, and also it reached to this 0.25 earlier than these cases. And considering about this experiment situations, when they're trying to make the membrane dry, it might happen that earlier time like this part. That means in the nylon cases, the bottle brush clusters has much planar and faster migration to this interface. And also we compute the context between the beads between the thermoplastics and the air.
5 minutes.
Okay, so for these cases, we compute the backbone beads with the thermoplastic and find that the bottle brushes backbones is more preferred for the PMMA case than the nylon case. And then we compute the number of the contacts between the side chains with this air. As I mentioned, the side chains represent for the PFP groups, which would be the lowest surface tension material in this case, and this is also plays the main role for the oil repulsing. So our simulation shows that for the nylon case, the side chains is more prefer the air than the PMMA case, which is in good agreement with our previous research. And these two plots is also shows that the bottle brush clusters has a faster migration dynamics in the nylon 6 case than the PMMA case. So goes to our conclusions. In this research, our collaborator finds that with the small amount of addition of bottle brushes, it would significantly improve the oil repulsion of the thermoplastics. And based on this experiment findings, they first develop a co-screening model for these fluorinated bottle brushes, and then they characterize the aggregations for the bottle brushes in different thermoplastic systems, and shows that for the nylon 6 cases, it has a much faster aggregation process and form more flat layers than the PMMA case. That might be the reason it has higher oil repulsion than the one in PMMA. And for this research, I would like to thank to the parameter cluster and the NSF fundings, and also I would thank to the conference. Thank you.
Thank you very much also, Dong. So yeah, the floor is now open for questions. Are there any questions?
I have a question, if I may.
Yeah, please.
Hold on, maybe I can turn my video. I'm thinking I'm curious about the applications of these kind of materials. And then I was involved some time ago in the zeolite synthesis. And I'm thinking, is it possible perhaps to find an application for that as a templating materials, for example, to direct some synthesis of zeolites or other porous materials?
You mean like this one for this bottle brushes?
Yes, for example, yes.
Yes, the where used one is like for this block bottle brushes, they could form a very ordered lamella faces. So that one is used in the phonemic one. And in our previous research, we also have these bottle brushes. They could make this conjugates like the domains. That cases, they could somehow protect the enzyme from the high temperature. That means somehow make this kind of microdomains in these cases, because this bottle brushes is actually quite large molecules in, compared to other polymers. So it's easy for it to make these phase separations. And it also make like micelles for drug deliveries.
Yes, exactly. Okay, thank you very much.
Thank you. Are there further questions? If not, then I would like to speak one more time to the speaker. Thank you very much for the very interesting presentation. So our morning session from today is closing. I would like, before closing it completely, two announcements. First of all, do not forget that we have an afternoon session starting at 5 o'clock, between 5 and 7 o'clock. We have very interesting talks where, again, we are going to speak about machine learning, Grand Canonical Monte Carlo, reactive force field, and also a lot about experimental methods and new experimental results. So please be sure to be there. On the internet, you can find the recorded talks for the subject in the evening and also the poster. So please have a look over them because it will make easier the interaction with the participants. And now the second announcement, we like to make a photo at the end of the session with everybody. So if please you could, open your videos and try to smile. We'd be happy to make a record of the participants. So we are going to start now. So smile. Thank you. We have to ask to do it 2 or 3 times because we have to go with all the participants. So once again, thank you. And one more time, please. Thank you very much. And let me see, we still have one more time to ask you. It is nice to see a lot of participants. I'll make the last one, I believe. Thank you. So thank you very much, everybody. We are looking forward to see you tonight from 5 o'clock. Please be there. And for those which do have contributions in the evening, do not forget, if you didn't submit the 2 slides, please do submit when submitted. Allow for the presentation of advertisement of your work. Thank you very much, everybody. Wish you a very nice afternoon and see you in the evening.
Thank you very much.
Bye.
Bye.
Bye-bye.
See you later.
So Juan, I think we can close. Yeah, I don't hear you anymore, but yeah, I think it's...
Oh, sorry. Yeah, I'm going to close and see you this afternoon.
Yeah. We log in at 4:30 or 4:45. What is the approach?
Let me see. It's a start at 5, so 4:45 is enough.
4:45 is perfect. Okay, I will send an email to everybody with the links so that we are sure that we have all the connection data.
Okay, perfect.
Okay, perfect. Thank you. Bye.
Bye.